Have you ever looked up at the night sky and wondered what keeps it all together? Those countless points of light, each one a distant sun or world, aren't just scattered randomly. They are part of an intricate cosmic choreography, moving with a precision that has captivated thinkers, dreamers, and scientists for thousands of years. It's a dance governed by rules so elegant and powerful that they shape not just our solar system, but the entire universe. And at the heart of this grand performance lies a field of study called celestial mechanics, the hidden framework that dictates how everything in the cosmos moves, interacts, and evolves. From the gentle, persistent pull of gravity that holds planets in their orbits to the subtle harmonies of orbital resonances that can stabilize or destabilize whole systems, these forces are the invisible hands guiding the fate of stars, galaxies, and even the universe itself. What's truly astonishing is that these principles aren't just abstract ideas. They touch everything we see when we gaze upward. The same forces that keep the moon circling Earth also govern the majestic swirl of distant galaxies. The same mathematics that predicted the return of Halley's Comet helps us navigate spacecraft across the solar system. For centuries, astronomers and physicists have worked to decode these patterns, from the early stargazers who mapped the heavens with nothing but their eyes and intuition to the modern scientists using space telescopes and supercomputers to probe the deepest mysteries of cosmic motion. Each discovery has peeled back another layer of this grand puzzle, revealing a universe that is both breathtakingly vast and astonishingly orderly. In this video, we're going to journey through the fundamentals of celestial mechanics, exploring how gravity shapes orbits, how momentum and energy interplay across immense distances, and how resonances create stability or chaos in planetary systems. We'll look back at the history of how humanity first began to understand these forces and forward to the cutting-edge questions that still mystify researchers today. By the end, I hope you'll not only grasp the science behind the motion of the cosmos, but also feel a deeper sense of connection to the elegant, clockwork-like beauty of the universe. So let's begin this exploration into the forces that govern the stars. To truly grasp the power of celestial mechanics, we have to rewind the cosmic clock and walk in the footsteps of the first stargazers. For millennia, humans looked up and saw a dome of fixed stars, with a few wanderers, the planets, moving in perplexing, looping paths against that backdrop. The ancient Greeks, with their passion for order and geometry, were among the first to try and impose a system on this celestial dance. Aristotle envisioned a universe of perfect, concentric crystalline spheres, with our imperfect Earth sitting motionless at the very center. This geocentric view was later refined by Ptolemy, who developed an incredibly complex model of epicycles, little circles upon bigger circles, to mathematically explain the planet's retrograde motion. It was a brilliant, if cumbersome, intellectual achievement that held sway for over 1,000 years because it matched what people saw with their own eyes. But the cracks in this Earth-centered universe began to show thanks to the painstaking observations of a Polish cleric named Nicolaus Copernicus. In the 1500s, he proposed a radical and heretical idea: what if the sun, not the Earth, was at the center? His heliocentric model was a monumental paradigm shift, instantly simplifying the solar system's architecture. It wasn't just a different arrangement, it was a completely new way of thinking about our place in the cosmos. Yet, Copernicus still clung to the idea of perfect circular orbits, which meant his model wasn't actually much more accurate than Ptolemy's at predicting planetary positions. The real breakthrough came from a German mathematician, Johannes Kepler, who was handed a treasure trove of precise observational data by the Danish astronomer Tycho Brahe. Kepler was a fervent believer in mathematical harmony, and he struggled for years to fit Tycho's data for Mars into a circular orbit. He finally had a stunning realization. The orbit wasn't a circle at all, but an ellipse with the Sun sitting at one focus. This was his first law of planetary motion, a complete departure from 2,000 years of astronomical tradition. His second law showed that a planet doesn't move at a constant speed, but sweeps out equal areas in equal times, speeding up as it gets closer to the Sun. And his third law established a precise mathematical relationship between a planet's orbital period and its distance from the Sun, proving the solar system was governed by a unified, predictable set of rules. These discoveries set the stage for one of the most iconic moments in scientific history. In the late 1600s, an Englishman named Isaac Newton watched an apple fall and saw not just a piece of fruit, but a connection. He realized the same force pulling the apple to the ground must extend outward, all the way to the Moon, keeping it in its orbit around Earth. From this profound insight, he formulated his law of universal gravitation, a single, elegant equation that could describe the force between any two objects with mass. Suddenly, Kepler's empirical laws weren't just descriptions. They were mathematical consequences of a universal force. Newton had provided the underlying mechanism, the why behind the motion. For the first time, the heavens and the Earth were united under one set of physical laws, opening the door to understanding not just our solar system, but the gravitational dance of the entire universe. This historical journey, from watching wanderers in the sky to unlocking a fundamental force of nature, is a powerful testament to human curiosity and our relentless drive to decode the cosmos. And so, with his law of universal gravitation, Isaac Newton gave us the mathematical key to the cosmos. That deceptively simple formula, F equals G times m1 times m2, all divided by r squared, is arguably one of the most profound statements ever written. It tells us that every single object that has mass exerts a gravitational pull on every other object. The strength of that pull depends on just two things: how much stuff the objects have their masses and how far apart they are. The bigger the masses, the stronger the pull, but distance is even more powerful because of that inverse square law. If you double the distance between two objects, the gravitational force isn't just cut in half, it becomes a quarter of what it was. Triple the distance and the force drops to a ninth. This sensitivity to distance is why we are glued to the Earth but don't feel any pull from the book on the other side of the room, and why the immense gravity of the Sun, 93 million miles away, can still hold our entire planet in a steady embrace. This law doesn't just explain orbits, it dictates their very shape. Remember Kepler's ellipses. Newton showed they are a natural consequence of this inverse square force. A planet is constantly falling toward the Sun, pulled by gravity, but it also has a tremendous amount of sideways momentum from its initial formation. The gravitational force acts as a centripetal force, continuously bending this forward momentum into a closed path. The perfect balance between the planet's inertia, its desire to keep moving in a straight line, and the Sun's relentless pull results in that elegant elliptical curve. The same physics applies to a moon orbiting a planet, a binary star system where two stars waltz around each other, or even our solar system's slow journey around the center of the Milky Way galaxy. But Newton's genius didn't stop at perfect two-body systems. His law also explains the beautiful imperfections and subtle complexities we observe. Planets don't orbit in isolation, they tug on each other. The gravitational influence of Jupiter, the solar system's heavyweight, causes slight deviations or perturbations in the orbits of the other planets. It was by meticulously tracking such a perturbation in the orbit of Uranus that astronomers in the 1800s were led to predict the existence and position of a new, unseen planet Neptune. This was a stunning validation of Newtonian mechanics. We discovered a world by the ghostly tug of its gravity on another. This universal force also creates some of the most dramatic phenomena in the universe, tides. The ocean's rise and fall is a direct product of gravity's pull weakening with distance. The Moon's gravity pulls more strongly on the side of Earth facing it than on the center of our planet, and more strongly on Earth's center than on the far side. This difference in force stretches the Earth, and its fluid oceans respond by bulging out on both the near and far sides. As Earth rotates through these two bulges, we experience high tides. The Sun contributes a smaller, modifying tidal effect, leading to the higher spring tides and lower neap tides we see throughout the month. From the gentle arc of a thrown ball to the majestic swirl of a galaxy, Newton's law of universal gravitation is the fundamental framework. It's the reason we can send a spacecraft on a multi-year, billion-mile journey to Pluto and have it arrive within a window of just seconds. It's the reason our moon is slowly drifting away from us, and why some moons elsewhere in the solar system are being sculpted by tidal forces into volcanic worlds. For over 2 centuries, this law was the ultimate description of gravity, a testament to the power of a single human mind to decipher the underlying order of the universe. It unified the cosmos, proving that the same physical laws operate on Earth and in the deepest reaches of space, forever changing our perspective and our potential. Yet, even with Newton's monumental achievement, we must never forget that he was standing on the shoulders of a giant, a man who first dared to find mathematical order in the messy, observed motions of the heavens. Johannes Kepler was a true visionary, a man driven by an almost spiritual belief that the universe was constructed with geometric perfection. But unlike the ancient Greeks, he was willing to let the data, the cold, hard numbers from Tycho Brahe's observatory, shatter his most cherished assumptions. For years, he wrestled with the orbit of Mars, trying to force it into a circular path. The math never quite worked. The planet stubbornly refused to follow the perfect circle that 2 millennia of astronomy had demanded. His breakthrough was one of the most courageous in scientific history. He abandoned the circle entirely. This led directly to his first law of planetary motion. The orbit of a planet is an ellipse with the Sun at one of the 2 foci. This was a revolutionary declaration. It demoted the Earth from any privileged position and did the same for the circle itself. An ellipse isn't a failed circle, it's a unique shape defined by its 2 focal points. The degree of its elongation, its stretch away from a perfect circle, is called its eccentricity. Most planetary orbits in our solar system have very low eccentricity. They're nearly circular, which is why it took so long to discover their true nature. But comets, for instance, follow wildly eccentric ellipses, diving in close to the Sun before flying back out to the distant reaches of the solar system. His second law, the law of equal areas, is perhaps even more counterintuitive. It states that a line joining a planet and the Sun sweeps out equal areas in equal intervals of time. Imagine a planet's elliptical orbit as a slightly squashed circle. Draw a line from the Sun to the planet. As the planet moves, this line carves out a pie-slice-shaped area. Kepler found that whether the planet is far away, moving slowly, or up close and racing along, that line will always sweep out the exact same amount of area over the same period, say 1 week. This means a planet's orbital speed is not constant. It's fastest at its closest approach to the Sun, a point called perihelion, and slowest at its most distant point, aphelion. Our own Earth, for example, moves several thousand miles per hour faster in January when it's nearest the Sun than it does in July when it's farthest away. But it was Kepler's third law that truly unified the solar system into a single, predictable clockwork. Published a full 10 years after the first two, it's often called the harmonic law because it reveals a precise mathematical relationship between the planets. It states that the square of a planet's orbital period, the time it takes to go around the Sun once, is proportional to the cube of the semi-major axis of its orbit. The semi-major axis is essentially the average distance from the planet to the Sun, or half the longest diameter of the ellipse. In practical terms, this law means that if you know how long a planet takes to orbit, you can calculate its exact distance from the Sun, and vice versa. It provided for the first time a true scale model of the solar system. Astronomers could now determine the relative distances of all the planets from the Sun with incredible accuracy, even if the absolute scale in miles wasn't yet known. The profound beauty of Kepler's laws is that they are purely descriptive. They describe how the planets move without initially explaining why. They were a set of brilliant patterns deduced from observation. It was Newton who later proved that these three laws are the inevitable mathematical consequence of a single, inverse square force of gravity acting between two bodies. Kepler gave us the what, and Newton provided the why. Today, these principles are not just historical footnotes, they are the active tools of modern astronomy. We use them to calculate the trajectories of every satellite and space probe, to predict the movements of asteroids, and to understand the orbits of distant exoplanets around other stars. Kepler's struggle to find harmony in the data gifted us with the first true map of the heavens, a set of rules that turned the cosmic dance from a mystery into a predictable, calculable performance. But to truly apply these laws of motion and gravity to the cosmos, we need a clean, solvable problem to start with, a sort of celestial laboratory where we can see the principles in their purest form. This is the essence of the two-body problem. Imagine isolating just two objects in the vast emptiness of space, a star and a single planet, or perhaps our Earth and the Moon, with nothing else around. Their only interaction is their mutual gravitational attraction. The question is, how will they move? Thanks to the work of Newton and those who followed, we have a beautifully complete and elegant answer. The two bodies will orbit around their common center of mass, a point called the barycenter. Think of the barycenter as the balancing point of the system. If the two objects have identical mass, this point would be exactly halfway between them. But if one is much more massive, like the Sun is compared to a planet, the barycenter lies very close to, or even inside, the larger object. Our entire solar system's barycenter isn't fixed at the Sun's exact center. It constantly shifts as the planets move, sometimes pulling it just outside the Sun's surface. In the Earth-Moon system, the barycenter is actually about 1,000 miles beneath the Earth's crust, which is why it appears from our perspective that the Moon orbits a stationary Earth. In reality, both are circling this shared point in space. The paths they trace are known as conic sections, the curves you get by slicing through a cone. The specific shape of their orbit depends entirely on the system's energy and angular momentum. If the bodies are gravitationally bound like a planet to its star, their relative path is a closed loop, an ellipse. This is the case for every planet in our solar system. If they have just enough energy to escape each other's pull, the path opens up into a parabola. And if they have more than enough energy, perhaps from a gravitational slingshot maneuver, the path becomes a hyperbola. This is the trajectory of many interstellar visitors, like the asteroid Oumuamua, which swung through our solar system and is now on a one-way trip back into deep space. The genius of solving the two-body problem lies in a mathematical trick called reduction. Instead of trying to track the complex dance of both bodies through space, we can redefine the problem. We can fix one body at the center of our coordinate system and study the motion of the second body relative to the first. This reduction transforms a very complicated two-object problem into a much simpler one-object problem, where we only need to solve a single differential equation. The solutions to this equation give us a powerful set of formulas, often called the orbit equations, that allow us to predict the exact position and velocity of one body relative to the other at any point in time, past or future. This isn't just abstract math, it's the absolute bedrock of modern space exploration. Every single satellite circling our planet, from GPS networks to weather monitors, follows an orbit calculated using these two-body solutions. When we send a probe to Mars, mission planners don't simulate the gravity of every single asteroid and moon. They primarily use a patched conic approximation. This technique breaks the journey into segments, each dominated by one primary gravitational body like Earth, then the Sun, then Mars, treating each leg as a separate two-body problem. It's a brilliant simplification that works with astounding accuracy. This framework is also essential for understanding binary star systems, where two stars orbit each other, often for billions of years. Of course, the pristine simplicity of the two-body problem is our idealization. The real universe is a messy place filled with countless gravitational influences. The moment you introduce a third body, a second planet, another moon, the elegant, closed-form solutions vanish, and the equations become famously difficult, if not impossible, to solve exactly. This is the notorious three-body problem, which introduces the potential for chaotic and unpredictable motion over long timescales. But that complexity doesn't invalidate the two-body solution, it elevates it. The two-body framework provides the essential starting point, the stable and predictable baseline from which we can begin to measure and understand the subtle, complex gravitational perturbations that make our cosmos so dynamic and fascinating. Now, the pristine elegance of the two-body problem gives us a perfect starting point, but the universe is never that simple or empty. In reality, every planet, moon, and spacecraft is constantly being gently nudged and tugged by the gravity of every other object in its vicinity. These tiny deviations from a perfect elliptical path are known as perturbations, and they are the subtle fingerprints of a crowded cosmos. While a single planet orbiting a lone star would follow Kepler's laws with clockwork precision forever, the presence of a third body, be it a nearby moon, a massive planet like Jupiter, or even a distant passing star, introduces a whisper of complexity that, over time, can rewrite the entire story of an orbit. To understand and predict these changes, astronomers developed a powerful branch of mathematics called Perturbation Theory. The core idea is brilliantly straightforward. Instead of trying to solve the impossibly complex many-body problem from scratch, we start with the perfect, solvable two-body orbit we already understand. We then treat all other gravitational influences as small, additive forces, tiny pushes and pulls that slightly perturb this ideal baseline. Mathematically, it's like making a series of minor adjustments to a known solution, recalculating the orbit's parameters over and over again to account for these external influences. This approach allows us to model the real, messy solar system with remarkable accuracy without getting lost in mathematical chaos. We can see the profound effects of perturbations everywhere we look. Jupiter, the solar system's gravitational titan, exerts a dominant influence. Its immense gravity significantly perturbs the orbits of the asteroids in the belt that bears its name, creating empty zones known as Kirkwood gaps where no asteroid can maintain a stable orbit because their periods would resonate with Jupiter's. Its pull also subtly alters the path of Mars, causing tiny but measurable shifts in the red planet's trajectory over centuries. Closer to home, the Moon's gravity doesn't just cause our tides, it also torques the Earth itself. Our planet's rotation is not perfectly upright. It spins on a tilted axis. The combined gravitational tug from the Moon and the Sun on Earth's equatorial bulge causes a slow, wobbling motion of this axis, much like a spinning top beginning to slow down. This phenomenon is called precession, and it takes about 26,000 years for Earth's axis to complete one full circle in the sky. This means the North Star, Polaris, won't always be our North Star. In a few thousand years, the axis will point toward a different star, Vega, gradually changing our celestial guideposts. The power of perturbation theory was proven in one of the most dramatic discoveries in astronomy, the prediction of Neptune. In the early 1800s, astronomers noticed that Uranus, the then most distant known planet, was not following its predicted path. Its orbit was being perturbed by an unseen mass. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently used these very principles to calculate where this mysterious perturbing body must be located. When astronomers pointed their telescopes to the spot Le Verrier predicted in 1846, they found Neptune, a stunning triumph of Newtonian gravity and perturbation theory that expanded the known boundaries of our solar system. This mathematical framework is not just about explaining the past, it is absolutely vital for our future in space. Precise orbital calculations for satellites and interplanetary probes must account for perturbations from the Moon, the Sun, and even the slight non-spherical shape of the Earth to maintain accuracy. When we plan missions that require gravity-assist slingshotting a spacecraft around a planet to gain speed, we rely on perturbation theory to plot a course where these gravitational kicks are predictable and beneficial, not chaotic. Ultimately, perturbation theory reveals a cosmos that is dynamic and ever-evolving. It shows us that stability in the solar system is not a permanent state but a delicate and temporary balance. The gentle, cumulative effects of these tiny forces can, over millions of years, dramatically alter orbits, potentially flinging planets into new arrangements or even ejecting them from their systems entirely. It's a humbling reminder that the clockwork universe, while predictable in the short term, holds deep, long-term rhythms of change that we are only just beginning to decipher. These gentle gravitational nudges we call perturbations are the background noise of the cosmos, but sometimes these interactions synchronize into something far more powerful and organized, a celestial harmony known as orbital resonance. This occurs when two or more orbiting bodies exert a regular, periodic gravitational influence on each other because their orbital periods form a simple numerical ratio. It's as if their motions are locked into a rhythmic dance, their gravitational pulls reinforcing each other at the same points in their orbits again and again. This repeated timed tug can have one of two dramatic outcomes. It can create an island of profound stability, locking worlds into safe, predictable paths for eons, or it can amplify chaos, destabilizing orbits and potentially flinging objects into the depths of space. One of the most famous and beautiful examples of a stabilizing resonance is the dance between Pluto and Neptune. For a long time, many people wondered how Pluto, with its orbit that crosses inside Neptune's path, could possibly avoid a catastrophic collision. The answer is a perfect 3-2 orbital resonance. For every 3 trips Neptune makes around the Sun, Pluto completes exactly 2. This synchronized timing means that whenever Pluto is at its closest point to Neptune's orbit, Neptune is always on the opposite side of the Sun. Their gravitational meeting times are choreographed by this ratio, ensuring they are never close to each other. It's a stunningly effective cosmic defense mechanism, a gravitational handshake that has kept the peace for billions of years. Perhaps an even more intricate celestial symphony is the one performed by three of Jupiter's largest moons, Io, Europa, and Ganymede. This is known as a Laplace resonance, a complex chain of gravitational locks. For every single orbit Ganymede makes around Jupiter, Europa completes exactly 2 orbits and Io completes exactly 4. This creates a precise 1:4 ratio. But this resonance does more than just prevent collisions. It actively shapes these worlds. The constant, regular gravitational squeezing from this orbital lock is the primary engine behind the intense volcanic activity on Io, the most volcanically active body in our entire solar system. That same tidal heating is also believed to maintain a vast global ocean of liquid water beneath the icy crust of Europa, making it one of the most promising places in our search for life beyond Earth. Here, resonance isn't just a mathematical curiosity, it's a world-building force, but not all resonances are so benevolent. In the asteroid belt between Mars and Jupiter, resonances with the giant planet create gaps known as Kirkwood gaps. In these zones, any asteroid that wandered in would have an orbital period that forms a simple ratio with Jupiter's, like 3 or 1 or 2 or 1. The repeated, periodic tug from Jupiter's gravity at the same point in its orbit would act like a push on a swing, adding energy over time. Instead of stabilizing the asteroid, this resonant kick would eventually perturb its orbit so dramatically that it would be ejected from the belt entirely. This is a powerful demonstration of how resonance can be a destructive, clearing force, sculpting the architecture of a solar system by removing material from certain zones. We see the creative power of resonance in stunning detail within planetary rings. The intricate structure of Saturn's rings, with their sharp edges, dark gaps, and braided patterns, is largely the work of tiny moons called shepherd moons. These moons orbit within or near the rings, and their gravitational influence resonates with the ring particles. For instance, the Cassini division, a prominent dark gap in Saturn's rings, is cleared out by a 2:1 resonance with the moon Mimas. Ring particles that would have orbited in that gap are given a gravitational kick every second orbit by Mimas, which pushes them out and maintains the gap's crisp boundary. The rings are, in effect, a live display of orbital resonances at work. The study of these phenomena has exploded beyond our solar system with the discovery of thousands of exoplanets. We now find entire planetary systems locked in resonant chains, often with multiple planets orbiting their star in perfect, synchronized ratios. This tells us that orbital resonance is not a quirky feature of our own solar system, but a fundamental process in planetary formation and evolution across the galaxy. By listening to these gravitational harmonies, we can infer the history of a system, how planets migrated inward or outward after they formed, gently steering each other into these stable, musical arrangements through their mutual gravitational influence. The universe is filled with these subtle symphonies, a hidden language of gravity that dictates stability, shapes worlds, and writes the long-term destiny of star systems. While the dance of gravity, orbits, and resonances provides the choreography for celestial motion, there's another, even more fundamental principle operating behind the scenes, a silent, unwavering rule that governs the spin of every planet, the swirl of every galaxy, and the very formation of solar systems. This principle is the conservation of angular momentum. In the simplest terms, angular momentum is the measure of an object's tendency to keep spinning or to keep moving along its curved path. Think of a figure skater pulling their arms in during a spin. they start to rotate much faster without any extra effort. That's conservation of angular momentum in action. The skater's mass is pulled closer to their axis of rotation, so to conserve this fundamental quantity, their spin rate has to increase. In the isolated vacuum of space, where there's virtually no friction to provide an external push or pull, this quantity remains perfectly constant. It is the reason why a planet, once set on its elliptical path around the Sun, will continue along that path indefinitely, and why a star, once born spinning, can continue to rotate for billions of years. This concept is the key to understanding one of the most beautiful and universal structures in the cosmos, the protoplanetary disk. Our solar system, and every other one we've observed, began not as a sphere, but as a vast, slowly rotating cloud of gas and dust. Under its own gravity, this cloud began to collapse inward, but because the cloud had even the tiniest amount of inherent spin, the law of conservation of angular momentum took over. As the cloud contracted, its radius decreased. To conserve its angular momentum, its spin had to increase, just like our figure skater. This increasing rotation caused the cloud to flatten along its axis of spin, resisting further collapse in that plane and forming a wide, pancake-like disk with a budding protostar at its hot, dense center. Within this spinning disk, dust grains could collide and stick together, eventually snowballing into planetesimals and finally, full-fledged planets, all orbiting in the same flat plane and in the same direction, a permanent fossil record of that initial spin. The entire architecture of our solar system, from the orderly orbits of the planets to the flatness of the asteroid belt, is a direct consequence of this one unbreakable law. We also see the profound effects of angular momentum exchange in systems where two bodies are gravitationally bound, like a planet and its moon. Over vast stretches of time, the gravitational tug between them can act as a kind of external torque, allowing them to trade angular momentum. This exchange often leads to a state called tidal locking, where the orbital period of the smaller body matches its rotational period. Our moon is the most familiar example. It takes the same amount of time to rotate once on its axis as it does to orbit the Earth, which is why we only ever see one side of it. But this process isn't a one-way street. The moon's gravity also pulls on Earth, and the transfer of angular momentum from Earth's rotation to the moon's orbit is actually causing our day to get longer by a tiny fraction of a second each century, while simultaneously pushing the moon about 1.5 inches farther away from us every year. In more extreme binary systems, like two stars orbiting each other, this angular momentum exchange can dictate their ultimate fate. If one star expands into a red giant, its outer atmosphere can be pulled toward its companion star. The angular momentum of this transferred gas doesn't just vanish. It can form a new, swirling accretion disk around the second star, or it can be ejected from the system entirely, carrying angular momentum away. In the most violent cosmic events, like the merger of two black holes, the incredible release of energy in the form of gravitational waves is a direct result of the system redistributing and losing angular momentum to settle into a new, stable state. The powerful chirp detected by observatories like LIGO is the sound of angular momentum being radiated across the fabric of space-time. From the grandest scales of galactic spirals to the intricate details of planetary rings, angular momentum is the silent, persistent architect. It is the reason why galaxies don't simply collapse into formless blobs, why Saturn's rings remain distinct and flat, and why our solar system is a disk and not a sphere. It is a fundamental property that was set in motion during the universe's earliest moments, and it continues to govern the structure, stability, and evolution of every rotating and revolving object we see in the night sky. Without this guiding principle, the cosmos would lack its beautiful order and dynamic motion, making it one of the most essential yet often overlooked forces in all of celestial mechanics. We've explored how gravity pulls and momentum spins, but one of its most fascinating and tangible effects is something we can witness right here on Earth every single day: the rhythmic rise and fall of the ocean tides. This daily miracle is a direct physical manifestation of gravity's gradient, the fact that its pull weakens with distance. This difference in force across an object is what we call a tidal force. It doesn't just move water, it stretches, squeezes, and sculpts worlds across the cosmos, driving some of the most dramatic and energetic processes we know. The principle is easiest to grasp close to home. The Moon's gravity pulls on our planet, but it pulls more strongly on the side of Earth facing the Moon than on the planet's center, and more strongly on the center than on the far side. This difference in force, however minute, tries to stretch the entire Earth. Our rigid planet resists this deformation, but our fluid oceans flow willingly in response, bulging outward on both the near side and the far side. As Earth rotates daily beneath these two oceanic bulges, any given coastline will experience two high tides and two low tides each day. The Sun plays a modifying role. When the Sun, Earth, and Moon align during the full and new moons, their gravitational tugs combine to create especially high spring tides. When they are at right angles during the quarter moons, their pulls partially cancel out, leading to the lower neap tides. This celestial tug of war is a perfect clockwork demonstration of gravity's differential nature. But the implications of tidal forces extend far beyond our shores into the realm of the truly extraordinary. Consider Jupiter's moon Io. This small world is caught in an incredible gravitational tug of war between massive Jupiter on one side and the resonant pulls of its sister moons, Europa and Ganymede, on the other. This constant, rhythmic squeezing and stretching flexes Io's entire interior. The friction from this relentless tidal flexing generates immense internal heat, melting rock and turning Io into the most volcanically active body in the entire solar system. Its surface a constantly changing landscape of erupting volcanoes and flowing lava lakes. Here, tidal forces aren't just moving liquid, they are fundamentally powering a world, turning what would be a cold, dead moon into a geological inferno. Tidal forces can also be incredibly destructive. When a small body, like a comet or an asteroid, ventures too close to a massive one, like a star or a planet, it experiences a tidal force so extreme that it can be torn completely apart. The side of the comet facing the star feels a vastly stronger gravitational pull than the side facing away. If the comet crosses a critical boundary known as the Roche limit, this difference in pull, the tidal force, overcomes the comet's own meager gravity and internal strength, shredding it into a stream of debris. We've observed this fate befall comets that strayed too close to our Sun, and astronomers believe it's a common way for planets to lose moons or for stars to dismantle and consume planets that spiral inward. The most extreme example of tidal destruction occurs near black holes, in an almost unimaginable process poetically termed spaghettification. An astronaut falling feet first toward a stellar mass black hole would feel an exponentially stronger gravitational pull on their feet than on their head. This tidal force would stretch their body into a thin stream of atoms, a single, long strand of matter spiraling into the oblivion of the event horizon. While this is a terrifying thought experiment, it underscores the raw power of gravity's gradient in environments of unimaginable density. On much longer, gentler timescales, tidal forces act as a cosmic brake, slowly but surely synchronizing orbits and rotations. The same tidal bulges raised on Earth by the Moon create a slight drag on our planet's rotation, gradually slowing it down and lengthening our day. but energy and momentum are always conserved. The angular momentum lost by Earth's spin is transferred to the Moon's orbit, causing it to slowly spiral outward, moving farther away from us year after year. This process has already reached its conclusion for the Moon itself. It is tidally locked, forever showing us only one face because its rotation has been perfectly synchronized with its orbital period. This same fate awaits Earth in the distant future, when our planet's rotation eventually slows to match the Moon's month-long orbit, leaving one side of Earth in perpetual daylight and the other in endless night, a final state of tidal equilibrium. From powering volcanoes to pushing moons away, and from shredding comets to locking planetary spins, tidal forces are a subtle yet profoundly powerful sculptor of solar systems, quietly shaping the destinies of worlds over billions of years. This elegant predictability of the two-body problem, however, shatters the moment we introduce just one more gravitational player. Welcome to the infamous three-body problem, a puzzle that has fascinated and frustrated mathematicians for centuries. Unlike its simpler cousin, the general three-body problem has no closed-form solution. There is no single, neat equation that can tell us the precise positions of three gravitationally interacting bodies for all time. Instead, the system descends into a realm of chaos and beautiful unpredictability, where the long-term fate of these celestial dancers becomes fundamentally uncertain. This chaos stems from a profound characteristic known as sensitivity to initial conditions. Imagine trying to predict the outcome of a game of cosmic pool with three balls. If you could measure their starting positions, masses, and velocities with infinite precision, you could, in theory, calculate their paths forever. But in the real world, our measurements always have a tiny, imperceptible margin of error. In a two-body system, that tiny error remains tiny in your predictions. But in a three-body system, that microscopic uncertainty doesn't just grow, it explodes exponentially. A difference in starting position as small as the width of a single atom can, over enough time, lead to a completely different outcome. One planet might be flung out of the system entirely, while the others settle into a tight binary pair. This is the essence of chaos, a deterministic system governed by strict laws that is nonetheless utterly unpredictable in the long run. We can see the fingerprints of this chaos throughout our solar system. While most systems are stable on human timescales, the gravitational interplay between the Sun, Jupiter, and Saturn, for instance, introduces subtle chaotic elements that make predicting the precise configuration of the solar system millions of years into the future impossible. For smaller bodies, the effect is far more dramatic. An asteroid orbiting in the main belt is not just influenced by the Sun. It feels the periodic tugs of Mars and the massive, disruptive gravity of Jupiter. Over millennia, these repeated perturbations can push it from a stable orbit into a new path that might eventually cross into the inner solar system, becoming a potential threat to Earth. Its ultimate destiny is a product of this chaotic gravitational dance. Faced with this mathematical intractability, scientists haven't surrendered, they've innovated. Since we can't solve the equations with pen and paper, we use the immense number-crunching power of computers to simulate these systems. By plugging in the best initial measurements we have, we can run numerical simulations forward in time to see probable outcomes. This is how we map the long-term evolution of solar systems and assess the impact risk of near-Earth asteroids. We also use clever simplifications, like the restricted three-body problem, where we assume one of the bodies has such a tiny mass that it doesn't gravitationally influence the two larger primaries. This model is perfect for studying the motion of a spacecraft, a comet, or a tiny asteroid under the influence of, say, the Sun and Jupiter. It is within this restricted model that we find rare and precious islands of stability amidst the chaos, the Lagrange points. These are 5 specific points in the orbital plane of 2 massive bodies where the combined gravitational forces and the centrifugal force of a smaller object's motion perfectly balance. At these points, a low-mass object can essentially park itself, moving in sync with the 2 larger bodies. The first 3 points, L1 through L3, are metastable like a ball balanced on a saddle. A small push will send it drifting away. But the L4 and L5 points, which lead and follow the smaller primary body in its orbit by 60 degrees, are truly stable. Here, objects can gather and remain for eons. We see this in our own solar system with the Trojan asteroids, which orbit in Jupiter's L4 and L5 points, forever trapped in a gravitational equilibrium with the giant planet and the Sun. The 3-body problem is more than a mathematical curiosity. It is a humbling reminder of the limits of prediction in a universe governed by strict physical laws. It tells us that our cosmic neighborhood is not a perfect, predictable clockwork, but a dynamic and ever-changing system where stability is often temporary and chaos is always lurking in the equations. This inherent complexity is what fuels cutting-edge research in celestial mechanics and dynamical astronomy today, as scientists use ever more powerful computers to simulate the birth and evolution of planetary systems, and to understand the delicate gravitational dances that can make or break a world. And so, in the complex and often chaotic gravitational dance of the 3-body problem, we find these extraordinary oases of calm, the Lagrange points. Named for the Italian-French mathematician Joseph-Louis Lagrange, who predicted their existence in 1772, these are 5 specific locations in space where the combined gravitational pull of 2 large masses and the centrifugal force of a smaller object's motion perfectly balance each other out. Imagine a spacecraft positioned at one of these points. It essentially orbits the larger system's center of mass, moving in lockstep with the smaller primary body, and requires very little energy to maintain its position. It's like finding a serene eddy in a rushing river, a place where an object can remain nearly stationary relative to the 2 larger bodies, held in a delicate gravitational equilibrium. Each of the 5 points, labeled L1 through L5, offers a unique set of characteristics. The first 3, L1, L2, and L3, are points of unstable equilibrium. Think of them like a marble balanced perfectly on the crest of a steep hill. It can sit there, but the slightest nudge, a small thruster firing from the spacecraft itself, or a gentle push from solar radiation pressure will send it drifting away. This means satellites parked here, like the Solar and Heliospheric Observatory at the Earth-Sun L1 point, or the James Webb Space Telescope at the Earth-Sun L2 point, must carry fuel for occasional small corrections to stay in their desired halo orbits around these points. Despite this need for minor station keeping, the energy savings are enormous compared to trying to hold a position elsewhere in space. The truly magical points, however, are L4 and L5. These form the 3rd points of 2 equilateral triangles, with the 2 large masses at the other vertices. Located 60 degrees ahead of and behind the smaller body in its orbit, L4 and L5 are regions of stable equilibrium. Now the analogy shifts from a marble on a hill to a marble resting at the bottom of a bowl. If perturbed, it will naturally drift back toward the center. This inherent stability means that objects can gather and remain at these points for eons, with gravity itself shepherding them back into place. We see this most spectacularly with the Trojan asteroids, which have been trapped for billions of years in the L4 and L5 points of Jupiter's orbit around the Sun, with one swarm leading the gas giant and another trailing behind it. Our own planet has its family of Trojans as well, and we've even begun to utilize these stable zones for our own exploration. The concept of a Lagrange point is no longer just a theoretical curiosity. It is a fundamental tool for 21st century astronomy and spaceflight. By placing an observatory like the James Webb Space Telescope at the Sun-Earth L2 point, we gain an immense advantage. This location, about 1.5 million kilometers beyond Earth, offers a perpetually unobstructed view of the deep universe, as the Sun, Earth, and Moon are all positioned in the same direction behind the telescope's massive sunshield. Furthermore, because the spacecraft orbits the L2 point rather than Earth itself, it maintains a relatively stable thermal environment and requires minimal fuel to maintain its position for its planned mission lifetime. Looking to the future, visionaries see Lagrange points as the interplanetary equivalents of way stations or harbors. The stable L4 and L5 points in the Earth-Moon system, for instance, have been proposed as ideal locations for future space stations, fuel depots, or construction yards for large spacecraft destined for Mars and beyond. Their natural stability would drastically reduce the cost and complexity of maintaining such outposts, making them the perfect stepping stones for humanity's expansion into the solar system. From providing a safe haven for ancient asteroids to offering a strategic vantage point for our most powerful telescopes, Lagrange points are a breathtaking demonstration of how understanding celestial mechanics allows us to find harmony within the chaos and harness the universe's own forces to explore it more effectively. But the elegant dance of two bodies isn't just a theoretical exercise or a framework for our solar system. It's the most common stellar arrangement in our galaxy. Look up on a clear night, and many of the points of light you see aren't single stars at all. They are binary systems, two stars locked in a mutual gravitational embrace, orbiting their common center of mass. In fact, more than half of all stars in the Milky Way are part of such a pair or even larger multiples, making our solitary sun something of an outlier. These cosmic duos are far more than just a curiosity. They are the universe's premier laboratories, offering astronomers a direct and powerful way to measure the properties of stars and test the very laws of physics under extreme conditions. The most fundamental gift a binary system provides is a direct method to weigh stars. Using Newton's and Kepler's laws, astronomers can carefully track the orbits of the two stars. By measuring the orbital period and the semi-major axis, the average distance between them, the law of universal gravitation, gives us the sum of their masses. If we can also determine the individual orbits of each star around the barycenter, we can calculate their mass ratio, allowing us to find the precise mass of each component. This is absolutely crucial because a star's mass is its destiny. It dictates its temperature, luminosity, lifespan, and ultimate fate. By studying binaries, we've built the entire mass-luminosity relationship that allows us to estimate the mass of single stars based on their brightness alone. They provide the cosmic scale against which all other stellar measurements are calibrated. Beyond just mass, these systems are also vital for measuring cosmic distances. For nearby eclipsing binaries where our line of sight is nearly in the plane of their orbit so that the stars periodically pass in front of each other, we can gather a treasure trove of data. By analyzing the precise details of the light dimming during these eclipses, we can determine the star's actual sizes, temperatures, and orbital parameters. Combining this with their apparent brightness gives us a highly accurate distance, making these systems fundamental rungs on the cosmic distance ladder that allows us to map the scale of our galaxy and beyond. The dynamics of a binary system are profoundly shaped by the distance between its stellar partners. In a wide binary, the two stars are separated by thousands of astronomical units. Their gravitational influence on each other is so gentle that they evolve almost entirely independently, like two distant neighbors living separate lives. But in a close binary, the stars can be separated by just a few stellar radii, and their proximity leads to a far more intimate and dramatic relationship. The gravitational pull can become so strong that it can distort the stars from perfect spheres into teardrop shapes, and in extreme cases, they can become tidally locked, with each star forever presenting the same face to its companion, much like our moon does to Earth. This close proximity can trigger one of the most spectacular events in stellar astrophysics, mass transfer. If one star in the pair evolves faster and expands into a red giant, its outer atmosphere can be pulled by gravity across the gap between them, spilling onto its companion. This stream of gas doesn't just fall directly onto the other star. Because of the conservation of angular momentum, it typically forms a spectacular, glowing accretion disk of superheated plasma around the receiving star. The consequences of this process are staggering. It can rejuvenate the receiving star, giving it a fresh supply of hydrogen fuel and altering its evolution. It can also trigger periodic cataclysms. If the recipient is a white dwarf, the accumulated hydrogen on its surface can ignite in a runaway thermonuclear explosion, causing a nova that can briefly outshine an entire galaxy. In even more extreme cases, if too much mass is dumped onto a white dwarf, it can push it over the Chandrasekhar limit, leading to a Titanic-type Aya supernova explosion that completely obliterates the star. These interactions reveal the ultimate fates available to binary systems. Some close pairs will gradually spiral inward over billions of years due to gravitational wave radiation until they finally merge, potentially creating a single, massive star or an exotic blue straggler. Others may end their lives as a binary pair of ultra-dense stellar remnants like two white dwarfs, two neutron stars, or even a neutron star and a black hole. It was the precise monitoring of such a binary pulsar, two neutron stars orbiting each other, that provided the first indirect evidence for the existence of gravitational waves, a discovery that would later earn a Nobel Prize. And the spectacular merger of two neutron stars, detected in both gravitational waves and light in 2017, confirmed that these incredible collisions are the cosmic forges where heavy elements like gold and platinum are created and scattered across the galaxy. From providing the basic tools to measure the universe to staging some of its most violent and creative phenomena, binary star systems are a testament to the dynamic and interactive nature of the cosmos. They show us that stars are not isolated beacons but social creatures, whose lives and deaths are often intertwined by gravity in a complex dance that shapes their evolution and enriches the galaxy with new elements and new mysteries to solve. Yet the serene orbits we see today are not the ones the planets were born into. They are the final products of a dynamic and often violent construction process that unfolded over hundreds of millions of years. This grand construction project began within the swirling, flattened protoplanetary disk of gas and dust that surrounded our infant sun. Tiny dust grains within this disk began to stick together, first through static electricity, then through gentle collisions, gradually snowballing into larger and larger bodies called planetesimals. As these planetesimals grew, their gravitational influence increased, allowing them to pull in more material and eventually clear their own paths around the sun, becoming the cores of the planets we know today. But this was far from a neat and orderly process. It was a chaotic demolition derby of collisions and gravitational encounters that ultimately sculpted the solar system's architecture. This early period of chaotic growth was followed by an even more dramatic phase known as the Grand Tack, a theory that suggests Jupiter played a massive role in reshaping the inner solar system. After forming much farther out, Jupiter is believed to have migrated inward, pulled by gravitational interactions with the gaseous disk. This inward journey would have scattered countless planetesimals, hurling some into the Sun and flinging others out into the outer solar system. Just as it approached the orbit of Mars, its inward migration was halted and then reversed by the gravitational pull of a newly forming Saturn, causing it to migrate back outward to its current position. This celestial dance, much like a sailboat tacking against the wind, explains so much about our solar system's oddities: why Mars is so small, the composition of the asteroid belt, and the existence of the rocky, terrestrial planets close to the Sun. This process of planetary migration isn't unique to our solar system. In fact, it's the key to understanding one of the biggest surprises in modern astronomy: the existence of hot Jupiters. When astronomers first began discovering exoplanets, they were stunned to find gas giants many times the mass of Jupiter orbiting incredibly close to their stars, completing a full orbit in just a few days. Our own Jupiter takes 12 years. These planets simply could not have formed in such scorching, gas-poor environments. They must have formed much farther out, in the cooler regions of their protoplanetary disks where ice and gas were plentiful, and then migrated inward over time. This migration is thought to be driven by two main mechanisms, either through gravitational drag against the leftover gas in the disk, which slowly pulls the planet inward, or through violent gravitational interactions with other planets, which can slingshot one planet inward while ejecting another entirely. The long-term gravitational interactions between planets don't end after the protoplanetary disk dissipates. They continue to gently tweak and refine orbits over billions of years. This is known as secular evolution, a slow, rhythmic change in the shape and orientation of an orbit. Earth's own orbit undergoes these cycles, with its eccentricity, how circular or elliptical it is, waxing and waning over periods of 100,000 years. These Milankovitch cycles are a primary driver of our planet's ice ages, as slight changes in the amount and distribution of sunlight can tip the global climate into a glacial period or an interglacial warm period. The gravitational influence of Jupiter is the main orchestrator of these slow, climatic rhythms, a subtle reminder that the planets are all connected in a vast gravitational web. The final architecture of a solar system is a frozen record of this violent and dynamic history. The asteroid belt between Mars and Jupiter is not a failed planet, but a region where Jupiter's immense gravity prevented any large body from ever forming, its chaotic perturbations keeping the material there stirred up and scattered. The Kuiper Belt beyond Neptune, home to Pluto and other icy worlds, is the scattered remnant of the solar system's initial construction, a ring of debris that was pushed outward by the migrating giant planets. Even the peculiar, highly tilted orbit of a planet like Uranus might be the result of a colossal impact with an Earth-sized object during the solar system's tumultuous youth. By studying these patterns, we are essentially doing celestial archaeology, piecing together the history of our solar system's formation from the clues left behind in the present-day orbits of planets and smaller bodies. This understanding completely reshapes our view of planets and their potential for life. A planet's orbit is its destiny, dictating its climate and therefore its habitability. A world that undergoes extreme orbital migration might be flung from the freezing outer regions into the warm habitable zone, potentially thawing a frozen ocean and creating conditions ripe for life. Conversely, a planet that is gravitationally kicked out of the habitable zone would see its oceans freeze solid. The dynamic evolution of orbits means that a star's habitable zone is not a fixed, static place, but a stage that planets can move onto and off of over astronomical timescales. As we search for life beyond our solar system, we must therefore look not just for planets that are in the right place today, but for systems with a stable architectural history that would allow a world to remain habitable long enough for life to arise and evolve. The story of orbital evolution is ultimately the story of whether a planet is given the enduring, stable conditions necessary to become a living world. For all the intricate rules and elegant equations we've explored so far, from Kepler's laws to the chaos of three-body problems, there remains a ghost in the cosmic machine, a mysterious, invisible force that governs the grandest scales of all. This is the influence of dark matter, a substance that defies everything we know about the tangible universe. It doesn't shine, reflect, or absorb light. It is completely and utterly dark. Yet, its gravitational signature is written across the entire cosmos, sculpting the motion of galaxies and holding the largest structures in the universe together. Its discovery was one of the most startling in all of astronomy, born from a simple, perplexing observation. Galaxies were spinning far too fast for their own good. The story begins in the 1930s with a brilliant and meticulous Swiss astronomer named Fritz Zwicky. While studying the Coma cluster, a vast gathering of thousands of galaxies, he made a shocking calculation. He could estimate the cluster's total mass by adding up the light from all its stars, but he could also measure the mass dynamically by observing how fast individual galaxies within the cluster were moving. The two numbers should have matched. They did not. The galaxies were zipping around so quickly that the gravitational pull from all the visible stars was utterly insufficient to hold the cluster together. By all rights, the Coma cluster should have flown apart eons ago. Zwicky concluded there must be a huge amount of unseen matter, which he called Dunkel Materie, or dark matter, providing the extra gravitational glue. His idea was largely ignored for decades, considered too radical. The case for this mysterious substance became undeniable in the 1970s with the work of astronomer Vera Rubin. She was meticulously mapping the rotation curves of spiral galaxies graphs that show how fast stars and gas orbit at different distances from the galactic center. According to Kepler's laws, which work perfectly for our solar system, stars farther from the center should orbit more slowly, just as Pluto moves much slower than Mercury. But Rubin found something completely different. The stars at the outer edges of galaxies were moving just as fast as those near the center. The rotation curves were flat, not falling off. This meant that the gravitational pull holding these outer stars in their high-speed orbits wasn't coming from the bright, central bulge of the galaxy. It had to be coming from something else, a massive, invisible halo of matter that extended far beyond the visible edge of the galaxy. This was the first direct, widespread evidence that galaxies are embedded within vast, massive spheres of dark matter, whose gravity dominates their dynamics. This dark matter halo isn't a minor component. It is the primary architectural feature of a galaxy. For a typical spiral galaxy like our Milky Way, the stars, gas, and dust that we can see represent only a tiny fraction of the total mass, perhaps 10 or 15%. The remaining 85 to 90% is this invisible dark matter, forming a spherical halo that envelops the entire luminous disk. It is this halo's immense gravitational field that dictates how stars orbit the galaxy, and on a larger scale, how galaxies move within clusters. Without this unseen anchor, galaxies would simply unravel, their outer stars flung into the intergalactic void by their own centrifugal force. Dark matter provides the stable gravitational scaffolding upon which the visible universe is built. Its influence extends far beyond individual galaxies, shaping the cosmos on the largest scales imaginable. The universe isn't a random scattering of galaxies. It's a vast cosmic web with immense filaments of galaxies stretching across billions of light years, connecting at dense nodes where huge clusters reside. This entire web-like structure is woven by gravity, and the primary source of that gravity is dark matter. Computer simulations of the universe's evolution show that if only ordinary matter existed, gravity would be far too weak to pull matter into such elaborate, large-scale structures in the time since the Big Bang. It is the gravitational pull of dark matter, which began clumping together immediately after the universe's birth, that provided the seeds for this cosmic architecture. Ordinary matter simply followed, flowing into the gravitational wells carved out by dark matter to eventually form the galaxies and stars we see today. So what is this stuff? That remains the multi-billion-dollar question. We know what it's not. It's not planets, asteroids, or failed stars made of ordinary atoms. We've ruled those out. The leading theory is that it is a new type of elementary particle, one that interacts via gravity and possibly the weak nuclear force, but not electromagnetism, which is why it doesn't emit or absorb light. These hypothesized particles are called WIMP, or weakly interacting massive particles. Dozens of ambitious experiments deep underground are searching for the incredibly rare recoil that would occur if one of these particles ever bumped into an atomic nucleus. Other theories propose different candidates, like actions, or even suggest that our understanding of gravity itself needs a fundamental revision on galactic scales, though this latter idea has struggled to explain all the observations. The hunt to identify dark matter is one of the most profound quests in all of science. Unlocking its nature wouldn't just solve an astronomical puzzle. It would represent a monumental leap in fundamental physics, potentially revealing a whole new sector of particles that make up the majority of the universe's mass. It forces us to accept a humbling reality. The universe we see, with all its glittering stars and majestic galaxies, is just the visible frosting on a much larger, darker, and mysterious cake. The forces of celestial mechanics, so precise and predictable within our solar system, operate on a galactic stage dominated by a ghost we cannot see, a reminder that the cosmos still holds its deepest secrets close. Yet for all its power and precision, Newtonian gravity, the very foundation of celestial mechanics for over 2 centuries, is not the final word. It is an incredibly accurate approximation for most of the universe, but it begins to fray at the edges, failing to explain the most extreme and subtle behaviors of space and time. This is where Einstein's theory of general relativity enters the stage, not Chinese letter Newton's work, but to complete it, revealing a far more bizarre and beautiful reality where gravity is not a force at all, but a property of space itself. Einstein's revolutionary idea was that mass and energy don't just create a force, they actually warp the very fabric of the universe, which is a 4-dimensional combination of space and time called spacetime. Imagine spacetime as a taut, flexible rubber sheet. Placing a heavy object like a star on that sheet creates a deep depression. Now, if you roll a smaller marble nearby, it won't travel in a straight line. Its path will curve inward, following the contour of the depression. The marble isn't being pulled by a mysterious force. It's simply following the shortest possible path through the curved geometry around the star. In this view, Earth isn't being pulled by the sun. It's following the geodesic, the straightest possible line in the curved spacetime that the sun creates. This elegant concept explains gravity not as an action at a distance, but as a consequence of geometry. One of the earliest and most powerful validations of this idea came from a tiny anomaly in our own solar system, the orbit of Mercury. For decades, astronomers had been puzzled by the planet's behavior. The point in its orbit where it comes closest to the Sun, called its perihelion, was slowly rotating around the Sun itself. Newtonian mechanics could explain most of this precession as being caused by the gravitational tugs from the other planets, particularly Venus and Jupiter. But there was a stubborn, tiny discrepancy left over, an extra 43 arcseconds of precession per century that no amount of planetary perturbation could account for. It was a minuscule amount, but it was real. When Einstein applied his new equations of general relativity, they predicted this exact extra precession perfectly. The intense gravity of the Sun, so close to Mercury, was curving spacetime just enough to cause this additional shift. It was a monumental moment, proving that Einstein's theory wasn't just abstract math. It described our physical reality with stunning accuracy. This warping of spacetime has an even more dramatic effect on light itself. Because light travels along the geodesics of spacetime, its path bends when it passes near a massive object. Einstein predicted that starlight grazing the limb of the Sun during a total solar eclipse would be deflected by a specific, calculable amount. In 1919, expeditions led by Arthur Eddington confirmed this prediction, making Einstein a global celebrity. Today, we see this effect on a colossal scale in the form of gravitational lensing, where the immense gravity of a foreground galaxy cluster acts like a cosmic magnifying glass, bending and distorting the light from galaxies far behind it, creating stunning arcs and multiple images that allow astronomers to map the distribution of both visible and dark matter. Perhaps the most mind-bending consequence of this spacetime curvature is gravitational time dilation. Time itself runs slower in a stronger gravitational field. A clock at sea level closer to Earth's center of mass will tick very slightly slower than a clock on a mountaintop. This isn't a mechanical error, it is a fundamental property of the universe. This effect is absolutely crucial for the operation of the global positioning system. The atomic clocks on GPS satellites orbit in a weaker gravitational field than clocks on the ground, which makes them run faster by about 45 microseconds per day. If this relativistic effect weren't meticulously corrected for, the entire system would accumulate errors of over 10 kilometers per day, rendering it useless within minutes. Our daily navigation relies entirely on the precise application of Einstein's theory. Near the most extreme objects in the universe, like neutron stars and black holes, these relativistic effects cease to be subtle corrections and become the dominant reality. The curvature of spacetime becomes so severe that not even light can escape from within a boundary called the event horizon. The phenomenon of frame dragging occurs, where a massive rotating object like a black hole literally drags the fabric of spacetime around with it, like a spinning spoon in a vat of honey. Orbiting objects are forced to corkscrew around the central mass, their paths dictated by the whirlpool of twisted spacetime. The recent first image of the black hole at the center of galaxy M87 and the ongoing detection of gravitational waves, ripples in spacetime itself caused by cataclysmic events like black hole mergers, are direct observations of these incredible phenomena, all predicted by general relativity over a century ago. This deeper layer of cosmic mechanics shows us a universe that is far more dynamic and interconnected than Newton could have ever imagined, where space and time are not a static stage but active, malleable participants in a continuous gravitational dance. And if the warping of spacetime is the stage, then gravitational waves are the vibrations that ripple across it, a direct and stunning consequence of Einstein's vision. These are not waves of light or sound, they are literal ripples in the fabric of spacetime itself, caused by the most violent and energetic events in the universe. Imagine the fabric of the cosmos as the surface of a still pond. If you were to suddenly dip your hand in and swirl it around, you would send out a series of waves across the water. In the same way, when massive objects accelerate, especially when they orbit each other and collide, they create a disturbance that propagates outward at the speed of light, stretching and squeezing space-time itself as it passes. The existence of these waves was a key prediction of Einstein's theory of general relativity in 1916, but he himself was doubtful they could ever be detected. The distortions they cause are almost unimaginably tiny. A passing gravitational wave from a distant cataclysm might change the distance between the Earth and the Sun by less than the width of a single atom. For decades, detecting such a minuscule signal seemed like a fool's errand. That all changed on September 14, 2015, when the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. After decades of development and refinement, they recorded the unmistakable chirp of a gravitational wave for the very first time. The signal was generated over 1.3 billion years ago by the final, frantic inspiral and collision of two black holes, each about 30 times the mass of our Sun, merging into one. In a fraction of a second, an amount of energy equivalent to 3 solar masses was converted into gravitational waves, rippling outward across the universe until they finally passed through our planet, moving the 4-kilometer long arms of the LIGO detectors by a distance 10,000 times smaller than the diameter of a proton. This detection didn't just confirm a century-old prediction. It flung open an entirely new window on the universe. Until that moment, almost everything we knew about the cosmos came from studying light across the entire electromagnetic spectrum from radio waves to gamma rays. But gravitational waves are a completely different messenger. They allow us to perceive events that are completely dark, invisible to any telescope. The merger of two black holes, for instance, emits no light at all. It is a purely gravitational event. Before LIGO, we could only infer the existence of such stellar mass black holes indirectly. Now we can hear them collide. We are essentially listening to the universe, tuning into the cosmic symphony of space-time vibrations. Each gravitational wave signal carries a wealth of information encoded in its shape, its frequency, and its amplitude. By analyzing the specific chirp, how the wave's frequency and amplitude increase as the objects spiral inward, scientists can determine the masses of the objects involved and their distance from Earth. This provides a powerful new way to measure cosmic distances independently of traditional methods. Furthermore, the way the waves ring down after the collision tells us about the properties of the newly formed black hole, testing the predictions of general relativity in the most extreme gravitational environments imaginable. It's like doing forensic science on a cosmic scale, reconstructing the entire event from the vibrations it left behind. Since that first detection, the field of gravitational wave astronomy has exploded. The LIGO and Virgo observatories have now detected dozens of events, painting a startling new picture of the population of compact objects in our universe. We've heard the collisions of black holes of all sizes, and in 2017 we witnessed a truly landmark event, the merger of two neutron stars. This collision was not only heard in gravitational waves, but also seen across the electromagnetic spectrum by telescopes around the world and in space. The observations confirmed that these incredible collisions are the cosmic forges where heavy elements like gold, platinum, and uranium are created and scattered into the galaxy, solving a mystery that had puzzled astronomers for decades. We are now truly in a new era of multi-messenger astronomy, where we can both see and hear the same cosmic events. As our detectors become ever more sensitive and new observatories are planned for space, like the Laser Interferometer Space Antenna LISA, we will be able to listen for even lower frequency waves. This will allow us to hear the mergers of supermassive black holes at the centers of galaxies, a sound that would have been building over billions of years. It could even allow us to detect the primordial gravitational waves generated in the first instance after the Big Bang, giving us a direct glimpse into the birth of the universe itself. Gravitational waves are the deepest voice of the cosmos, a fundamental vibration that connects us to the most powerful forces shaping existence, and we have only just begun to learn the language they speak. These breathtaking cosmic events, where day turns to night or the moon glows a deep copper red, are not mystical portents but precise demonstrations of celestial mechanics in action. They are the ultimate product of alignment, distance, and motion, a celestial clockwork so exact that we can predict eclipses centuries into the future and millennia into the past. At its heart, an eclipse is a shadow play on the grandest stage, and to understand it, we need to consider the players: the Sun, a light source nearly 400 times larger than our Moon, the Moon itself, a solid sphere, and our Earth, the stage upon which the shadow falls. The reason these three bodies can create such a perfect illusion of similar size in our sky is a staggering coincidence of nature. While the Sun is about 400 times wider than the Moon, it also happens to be almost exactly 400 times farther away. This perfect proportionality means both disks appear to be almost the same size from our vantage point, setting the stage for the Moon to just barely cover the Sun during a total solar eclipse. A solar eclipse is a lesson in shadows and perspective. It occurs exclusively during a new moon, when the Moon is positioned directly between the Earth and the Sun. But because the Moon's orbit is tilted by about 5 degrees relative to Earth's orbit around the Sun, this alignment doesn't happen every month. Most new moons see the Moon passing either above or below the Sun from our viewpoint. Only when the new moon occurs at or very near one of the 2 points where its orbit crosses the ecliptic plane called a node does everything line up perfectly. When this happens, the Moon casts its shadow out into space, and if Earth is in the right place to intercept that shadow, viewers in the shadow's path witness an eclipse. The Moon's shadow consists of 2 distinct parts: the umbra, the central cone of pure, total shadow where all direct sunlight is completely blocked, and the surrounding penumbra, a region of partial shadow where only some of the Sun's light is obscured. The experience of the eclipse depends entirely on where you stand within this shadow. If you are within the path of the umbra, which is never more than about 270 kilometers wide and often much narrower, you will witness the jaw-dropping spectacle of a total solar eclipse. The Moon slides perfectly over the Sun, the sky darkens to a deep twilight, the temperature drops suddenly, and the Sun's magnificent corona, its wispy outer atmosphere, becomes visible as a shimmering halo of pearly white light. This totality lasts only a few precious minutes because the Moon's shadow is racing across Earth's surface at over 1,600 kilometers per hour. Outside this narrow path of totality, but within the much broader penumbral shadow that can span thousands of kilometers, observers see a partial eclipse where the Moon appears to take a bite out of the Sun. There's also a third, more rare type called an annular eclipse. This occurs when the Moon is near apogee, the farthest point in its elliptical orbit around Earth. At this distance, its apparent size is slightly too small to completely cover the Sun's disk. When it passes in front, a brilliant ring, or annulus, of sunlight remains visible around the dark silhouette of the Moon, creating a stunning ring of fire effect in the sky. A lunar eclipse offers a different perspective on the same celestial alignment, with the roles of shadow caster and viewer reversed. This event can only happen during a full moon, when Earth is positioned directly between the Sun and the Moon. Again, the 5-degree orbital tilt usually prevents this, causing the full moon to pass above or below Earth's shadow. But when a full moon occurs at a node, the moon glides right into Earth's shadow. From our viewpoint on the night side of the planet, we see the Earth's shadow begin to creep across the bright face of the full moon. Unlike the moon's small, sharp shadow, Earth's shadow is large enough to envelop the entire moon. A lunar eclipse also has umbral and penumbral phases, but the most dramatic sight is the total lunar eclipse, when the moon is completely immersed in Earth's umbra. But it doesn't disappear completely. Instead, it often glows with a spectacular coppery red or orange hue. This happens because Earth's atmosphere acts like a lens, bending and scattering sunlight. Our atmosphere filters out the shorter wavelength blue light and allows the longer wavelength red light to pass through, projecting a sunset glow onto the moon's surface. The exact color and darkness of the eclipsed moon can vary dramatically depending on the amount of dust and volcanic ash in Earth's atmosphere at the time, serving as a kind of global atmospheric health report. The ability to predict these events with pinpoint accuracy is one of the greatest triumphs of celestial mechanics, and it hinges on a cycle known as the Saros. The ancient Babylonians and later the Greeks noticed that eclipses tend to repeat in a pattern every 18 years, 11 days, and 8 hours. This Saros cycle exists because after this period, the Sun, Earth, and Moon return to almost exactly the same relative geometry. The cycle accounts for the time it takes for the Moon to complete a whole number of orbits and for the Sun to return to the same node of the Moon's orbit. That extra 8 hours, however, means that the Earth has rotated by about 120 degrees, so the path of the eclipse shifts westward by 1/3 of the globe each cycle. A given Saros series, which includes about 70 or so eclipses over more than 1,000 years, will begin with a partial eclipse at one of the poles, see its path migrate across the globe over centuries, and eventually end with a partial eclipse at the opposite pole. We are currently tracking dozens of active Saros series, each with its own unique history and future, allowing astronomers to map out every eclipse for generations to come. Beyond their predictable beauty, eclipses have also served as crucial scientific opportunities throughout history. The sudden darkness of a total solar eclipse allows astronomers to study the Sun's faint corona, which is normally overwhelmed by the brilliant photosphere. It was during an eclipse in 1919 that observations of starlight bending around the Sun provided some of the first evidence supporting Einstein's theory of general relativity. Even today, eclipses offer a unique window into the Sun's complex magnetic fields and the physics of its outer atmosphere. A lunar eclipse, while more subtle, provides a moment to reflect on our own planet's place in space, as we literally see the curved shadow of our world glide across the face of the Moon, offering ancient proof that we live on a spherical body. These alignments are more than just shadows. They are cosmic coincidences that have driven scientific discovery, inspired human awe for millennia, and given us a profound appreciation for the clockwork precision of our place in the solar system. This profound understanding of gravity and motion is not just academic. It is the very engine of our exploration, the invisible hand that guides every spacecraft we send into the void. The entire enterprise of spaceflight, from placing a simple communications satellite in Earth orbit to sending a probe on a multi-billion-mile journey to the outer planets, is an applied masterclass in celestial mechanics. It transforms the abstract laws of Newton and Kepler into a practical toolkit for cosmic navigation, allowing us to accomplish incredible feats with astonishingly limited resources. primarily because we have learned to use the gravity of celestial bodies as our propellant. One of the most brilliant and fuel-efficient techniques born from this understanding is the Hohmann transfer orbit. Imagine you want to move a spacecraft from a lower circular orbit to a higher one, say from Earth to Mars. The most intuitive idea might be to simply point your engines at Mars and fire, but that would be incredibly wasteful. Instead, we use a Hohmann transfer, which is an elliptical orbit that is tangent to both the original circular orbit and the target circular orbit. The maneuver is beautifully simple, just two precise engine burns. The first, short burst accelerates the spacecraft at just the right point in its lower orbit, kicking it onto the elliptical transfer path. The craft then coasts for months, following Kepler's laws, speeding up as it falls toward the inner solar system and slowing down as it climbs out, all without using a drop of fuel. Once it reaches the farthest point of its ellipse, the apopsis, which is perfectly aligned with the target planet's orbit, a second, short braking burn circularizes the orbit, matching the spacecraft's speed to its new destination. This elegant orbital dance is the fundamental highway of interplanetary travel, a cosmic freeway on-ramp that maximizes payload and minimizes the immense cost of launching fuel from Earth. But for missions to the outer solar system, even the efficient Hohmann transfer isn't enough. The distances are too vast and the energy required is too great. This is where celestial mechanics provides its most spectacular magic trick, the gravitational slingshot or gravity assist. This maneuver allows a spacecraft to steal a tiny fraction of a planet's orbital momentum to dramatically increase its own speed without expending any propellant. The principle is a fantastic demonstration of energy conservation. As a spacecraft approaches a planet, it falls into the planet's gravitational well, accelerating as it gets closer. It then swings around the planet's far side and is flung back out, decelerating as it climbs out of the gravity well. Crucially, because the planet itself is moving rapidly along its own orbit around the Sun, the net effect is a significant change in the spacecraft's speed and direction relative to the Sun. It's like throwing a tennis ball at the front of a moving train. The ball rebounds with much more energy than it had initially because it interacted with a massive, moving object. The Voyager missions are the legendary exemplars of this technique. Their grand tour of the outer planets in the 1970s and 80s was only possible because of a rare planetary alignment that allowed them to use each successive world, Jupiter, Saturn, Uranus, and Neptune, as a gravitational stepping stone. Each slingshot not provided a speed boost but also precisely aimed the spacecraft toward its next target. Without these assists, the journey to Neptune would have taken over 30 years instead of 12. The Cassini mission to Saturn used a series of gravity assists from Venus, Earth, and Jupiter to carry the massive orbiter and its fuel load all the way to the ringed planet. Even the New Horizons mission to Pluto, the fastest spacecraft ever launched, still required a final gravity assist from Jupiter to shave years off its travel time. These missions are triumphant validations of celestial mechanics, proving that by understanding the gravitational dance, we can hitch a ride across the solar system. Beyond interplanetary travel, these principles are vital in our own celestial backyard. The precise placement of satellites, whether for GPS, weather monitoring, or telecommunications, requires meticulous calculations to account for Earth's slightly non-spherical gravity and the perturbations from the Moon and Sun. The International Space Station must regularly fire its thrusters to maintain its orbit, fighting against the faint but persistent drag of Earth's upper atmosphere. And as we look to the future, to establishing a permanent presence at the lunar Lagrange Points or navigating the treacherous terrain of near-Earth asteroids, our success will hinge on this same deep knowledge. We are even using celestial mechanics to address the growing problem of space debris, calculating how to nudge defunct satellites into graveyard orbits or deorbit trajectories using minimal fuel. From predicting the path of a solar probe to planning a human mission to Mars, every single aspect of our journey off this planet is guided by the timeless, universal laws first glimpsed by stargazers millennia ago, now enabling us to become stargazers ourselves, venturing out into the cosmic ocean they could only dream of exploring. But this elegant clockwork we see today, this predictable dance of planets that has persisted for over 4 billion years, begs a profound and almost unsettling question. Is it built to last? When we project the motions of our solar system forward not for centuries but for billions of years, does this cosmic harmony hold, or does it eventually descend into chaos? The short answer, gleaned from some of the most powerful computer simulations ever run, is that our solar system is stable but only up to a point. It exists in a state of resilient fragility, where the vast scales of time can allow even the tiniest of nudges to accumulate into dramatic change. The inner solar system, home to Mercury, Venus, Earth, and Mars, appears to be a bastion of relative calm. The orbits of these rocky worlds are remarkably steady over gargantuan timescales. Their gravitational interactions, while constant, are small and tend to average out over long periods, creating a kind of dynamic equilibrium. This long-term stability is arguably one of the most important prerequisites for the development and persistence of life. A planet whose orbit wildly fluctuates in eccentricity would experience extreme climatic swings, making it incredibly difficult for a stable biosphere to take root and evolve over billions of years. The fact that Earth's orbit has remained within a fairly narrow, habitable zone for so long is not a guaranteed cosmic right. It's a fortunate product of this intricate gravitational balance. Venturing outward, however, the story begins to shift. The outer solar system, dominated by the gas giants, is a different gravitational landscape altogether. While their orbits seem steady on human timescales, numerical simulations that model their complex interactions over billions of years reveal a much more dynamic and uncertain future. The immense gravity of Jupiter and Saturn, in particular, engage in a slow, rhythmic gravitational conversation. Their most significant interaction is linked to a resonance between their orbits. Jupiter orbits the Sun almost exactly 5 times for every 2 orbits of Saturn. This 5-2 resonance is a major driver of long-term secular evolution in the entire system. While it doesn't cause instability on short timescales, it introduces a low-frequency beat that can very slowly pump energy into the system, potentially leading to larger orbital changes for the ice giants, Uranus and Neptune, over tens of billions of years. The greatest wild card in this long-term forecast isn't one of the planets, but the countless smaller bodies that weave through the system. Every time an asteroid or a comet makes a close pass by a planet, a tiny exchange of energy and momentum occurs. These individual interactions are minuscule, but over astronomical timescales, they act like a form of gravitational diffusion, a slow leakage of orbital certainty. This is especially true for objects in the Kuiper Belt and the scattered disk, whose chaotic orbits can be perturbed, eventually sending them inward to stir up the gravitational pot of the inner planets. This constant rain of small perturbations acts as a background noise of instability, a reminder that the solar system is not a closed, perfect system but an open one, constantly subject to influence from its smaller constituents. Perhaps the most dramatic external factor is the occasional close pass of another star. Our Sun, like all stars in the galaxy, is on its own orbit around the Milky Way. Every so often, perhaps once every 100 million years on average, another star passes relatively close to our solar system, within a few tens of thousands of astronomical units. While still a vast distance, the gravitational influence of a passing star can be enough to perturb the delicate cloud of comets in the Oort cloud, sending a shower of new comets inward. In rarer, closer encounters, a star could potentially gravitationally tug on the planets themselves, particularly the outer ones, altering their orbits in ways that could ripple through the entire system and destabilize the inner worlds. Our solar system's journey through the galaxy is not a solitary one. It's a voyage through a stellar neighborhood, and our neighbors can sometimes come a little too close for comfort. This entire field of study is a breathtaking blend of deep mathematics, advanced physics, and cutting-edge computational power. Scientists run what are called n-body simulations, where they program the initial positions, velocities, and masses of all major bodies, and then let the laws of gravity play out forward in time. Because of the chaotic nature of the system, they don't run just one simulation. They run thousands, each with slightly varied starting conditions to account for our imperfect knowledge. This allows them to calculate probabilities rather than certainties, painting a statistical picture of our solar system's future. The results suggest that while outright planetary collisions are exceedingly rare over the next 5 billion years, significant orbital eccentricity changes are not. Mercury, with its small mass and vulnerable position, has a small but non-zero probability of being ejected from the solar system entirely or even colliding with Venus in the distant future. Ultimately, studying the stability of our own cosmic backyard is about more than just celestial curiosity. It provides a universal framework. The lessons we learn about how gravitational interactions, resonances, and perturbations play out over time are directly applicable to the thousands of exoplanetary systems we are now discovering. It helps us understand which systems are likely to be long-lived havens for life and which are destined for chaotic rearrangements. It teaches us that a planet's location is not just a point in space, but a point in an ever-evolving gravitational story. A story that determines whether a world will be a stable home for billions of years or a temporary waypoint in a constantly shifting cosmos. Our solar system's apparent permanence is a snapshot in an immensely long movie, and we are only just beginning to understand how the plot might unfold. For centuries, our entire understanding of planetary systems was built on a single data point, our own solar system. We assumed that other star systems would look much like ours, rocky worlds close to the Sun, gas giants farther out, all orbiting in nearly the same flat plane and following well-behaved circular paths. The discovery of the first exoplanets orbiting a Sun-like star in the 1990s shattered that comfortable assumption and unveiled a cosmos of staggering diversity and bizarre orbital mechanics that we never could have predicted. We now know that our orderly solar system is not the rule, but perhaps the exception, and the study of exoplanets has thrown the field of celestial mechanics into a thrilling new era of discovery and mystery. One of the most shocking early finds was the class of planets now known as hot Jupiters. These are gas giants, often more massive than Jupiter, but they orbit breathtakingly close to their host stars, completing a full revolution in just a few Earth days. This immediately presented a colossal puzzle. According to our models of planet formation, a giant planet simply cannot form that close to a star. The protoplanetary disk there is too hot for ices to condense, and there isn't enough solid material to build such a massive core. The inescapable conclusion is that these planets did not form where we see them. They formed much farther out, in the cooler regions of their systems where building materials were plentiful, and then they migrated inward. This migration is thought to happen through one of two primary mechanisms. In the early life of a system, the planet can gravitationally interact with the gaseous disk itself. creating spiral density waves that act like a brake, slowly sapping the planet's orbital energy and causing it to spiral inward over millions of years. Alternatively, a planet can be violently scattered inward by a gravitational kick from another massive planet, like a game of cosmic billiards, eventually settling into a tight, scorching orbit. Beyond these bloated giants, we find systems that defy our solar system's sense of personal space. Some stars host what are called tightly packed planetary systems, where multiple planets, often larger than Earth but smaller than Neptune, orbit their star closer than Mercury orbits our Sun. The gravitational dance within these systems is incredibly complex and finely tuned. The planets are so close together that their mutual gravitational influences are enormous, constantly tugging and perturbing each other's orbits. Yet many of these systems are stable, often locked into precise orbital resonances. A famous example is the System TRAPPIST-1, a cool red dwarf star with 7 Earth-sized worlds. Their orbits are so compact that they could all fit inside the orbit of Mercury, and they are locked in a long, intricate resonant chain, their orbital periods forming near-perfect ratios with one another. This gravitational harmony is what keeps the system from tearing itself apart, a delicate celestial ballet happening in an impossibly small region of space. On the opposite end of the spectrum, we find planets on wildly eccentric orbits, paths that are not neat circles or gentle ellipses, but are instead stretched into long, thin ovals. In our solar system, Mercury has the most eccentric orbit, but it's still relatively mild. Some exoplanets have eccentricities so high that they experience extreme temperature swings, roasting when they scream past their star at periastron, and then freezing solid at the distant, slow-moving part of their orbit. Such dramatic paths are almost always the signature of a violent past. A close gravitational encounter with another planet, or perhaps a stellar binary companion, can act like a slingshot, flinging a planet into a new, stretched-out trajectory. These discoveries tell us that many planetary systems undergo a chaotic, unstable youth, with giant planets scattering smaller worlds every which way before eventually settling down into a more stable configuration, often with the casualties of this gravitational warfare ejected into the cold darkness of interstellar space. The ultimate test of our celestial mechanics models comes from the most unexpected configurations, like planets sharing an orbit. We see hints of this in our own solar system with Jupiter's Trojan asteroids, which lead and trail the gas giant at its stable Lagrange points. But the possibility of a true co-orbital planet, a same-sized world sharing an orbit with another, is a mind-bending concept that astronomers are now actively hunting for. Another exotic arrangement is a planet orbiting a binary star system, the famous Tatooine-like world from science fiction. Real examples of these circumbinary planets exist, and their orbital stability is a delicate balancing act. The planet must orbit far enough from the binary pair to avoid being gravitationally kicked out, yet its path is constantly tweaked by the wobbling gravitational field of the two central stars. Understanding these orbits pushes our mathematics to the absolute limit, requiring complex simulations to map out the stable zones within such a dynamic environment. Every new exoplanet discovery from the James Webb Space Telescope and other observatories adds another piece to this grand puzzle. These aren't just new worlds, they are individual data points in a vast experiment on planetary formation and orbital dynamics. By building a statistical census of these systems, how many hot Jupiters exist, how common resonant chains are, the distribution of orbital eccentricities, we can begin to reverse engineer the life story of a typical planetary system. We can determine which formation and migration pathways are common and which are rare. This, in turn, refines our search for worlds that might be truly Earth-like, not just in size but in their orbital stability and climatic consistency. A planet on a wildly eccentric orbit is unlikely to be a haven for life, while one in the tranquil, habitable zone of a quiet star with circular orbit has a much better chance. The study of exoplanetary mechanics is therefore more than an academic exercise. It is the foundation of astrobiology, helping us pinpoint where we should focus our efforts in the monumental search for life elsewhere in the universe. Far beyond the familiar orbits of the planets, beyond even the distant, icy realm of the Kuiper Belt, lies the true final frontier of our solar system, a place so vast and remote it defies easy comprehension. This is the Oort cloud, a gigantic spherical shell of icy planetesimals enveloping our entire planetary system, stretching from roughly 2,000 astronomical units all the way out to a staggering 100,000 O. To grasp that distance, consider that a single astronomical unit is the span from the Earth to the Sun. This means the outer edge of the Oort cloud is nearly a quarter of the way to the very closest star, Proxima Centauri. This isn't a dense, swirling belt of material. It's an incredibly sparse and diffuse reservoir of perhaps trillions of frozen objects, each one a pristine relic from the solar system's violent birth over 4.5 billion years ago. The existence of this distant cloud was first proposed by the Dutch astronomer Jan Oort in 1950, not because anyone could see it, but because the mechanics of comets demanded it. He realized that the long-period comets, those that take thousands or even millions of years to complete a single orbit, were arriving from all directions in the sky, not just from the flat plane of the solar system. This isotropic distribution pointed to a spherical source, a vast storage cloud where these icy bodies have been held in a deep freeze since the dawn of our planetary system. The Oort cloud is the Sun's gravitational fingerprint at its absolute limit. It marks the outermost distance where an object can still be gravitationally bound to our star and not be pulled away by the gentle tidal forces of the galaxy itself. For an object in the outer Oort cloud, the Sun's gravitational grip is incredibly tenuous. Its orbit is so vast and slow that a single journey around the Sun could take millions of years. These objects exist in a state of delicate balance, and it doesn't take much to upset that balance and send them on a new trajectory. The primary mechanics that dislodge these comets and send them diving toward the inner solar system are the subtle, persistent tugs from the galaxy around us. As our solar system orbits the center of the Milky Way, it doesn't travel in perfect isolation. Occasionally, another star will pass relatively close by within a few light years, and its gravity can provide just enough of a nudge to perturb a distant Oort cloud object, altering its path. Even the collective gravitational gradient of the entire galaxy, known as galactic tides, acts like a slow cosmic hand, constantly stirring this icy reservoir and occasionally flipping a comet inward onto a new path. Once a comet is kicked loose from its sedentary life in the Oort cloud, it begins an epic journey governed by the same Keplerian laws that rule the planets, but on a mind-boggling scale. Its new orbit is typically a wildly elongated ellipse, bringing it screaming into the warmth of the inner solar system for a brief, spectacular visit before it swings back out to the deep freeze for another long hiatus. As it approaches the Sun, the story of its motion becomes more complex than simple two-body mechanics. Solar radiation begins to vaporize its icy surface in a process called outgassing, creating the glorious coma and iconic tail that make comets so breathtaking to watch. But this outgassing acts like a natural thruster. Jets of gas and dust shooting off the comet's surface impart a small but measurable non-gravitational force that can subtly alter its trajectory. For astronomers trying to predict a comet's path with extreme precision, especially for a potential close encounter with Earth. Accounting for these non-gravitational forces is an essential and challenging part of the calculation. A comet's path can also be dramatically reshaped by the planets it passes, particularly the gas giants. Jupiter, with its immense gravity, acts as the solar system's primary comet deflector. It can capture incoming long-period comets, pulling them into shorter, periodic orbits around the Sun, as it did with the famous comet Hale-Bopp. Conversely, it can also give a comet a gravitational kick, either ejecting it from the solar system entirely or hurling it back toward the Oort cloud on a new multi-million-year journey. These planetary encounters are a key part of the orbital mechanics that determine a comet's ultimate fate, acting as gravitational gates between the inner solar system and the outer darkness. Studying the mechanics of these icy visitors is about far more than predicting their paths. It is a form of celestial archaeology. Comets are time capsules, pristine leftovers from the protoplanetary disk that formed the planets. Their ices contain water and complex organic molecules, the very raw ingredients that were likely delivered to the early Earth, potentially seeding our world with the water in our oceans and the building blocks of life. By analyzing their composition and tracing their orbits back in time, we can learn not only about the Oort cloud itself, but also about the formation and early migration of the giant planets, whose gravitational influence originally scattered these objects to such incredible distances. The Oort cloud is the solar system's ultimate archive, and every comet that visits us is a page from that ancient record, delivered to our doorstep by the precise and dynamic laws of celestial motion. Yet after exploring the serene orbits of comets in the distant Oort cloud, we must now turn our gaze inward toward the vibrant and chaotic heart of our own galaxy, where the rules of celestial mechanics are pushed to their absolute limit. The center of the Milky Way is a place of unimaginable density and motion, a cosmic maelstrom dominated by a single, invisible titan, a supermassive black hole known as Sagittarius, a star. This colossal object, containing over 4 million times the mass of our Sun, is the silent gravitational anchor around which our entire galaxy slowly turns. For decades, its presence was only a theory, but thanks to some of the most precise astronomical observations ever conducted, we now have direct visual proof of its existence and overwhelming influence, all by watching the frantic dance of stars caught in its irresistible grip. The key to this discovery has been patience and precision. Watching the same patch of sky for decades, astronomers have focused powerful telescopes on the galactic center, patiently tracking the motions of individual stars that venture perilously close to Sagittarius, a star. The most famous of these is a star called S2. Its orbit is a breathtakingly tight ellipse that brings it within just 17 light hours of the black hole's event horizon. At its closest approach, S2 is moving at a staggering 15,000 kilometers per second. That's about 5% the speed of light, completing a full orbit in a mere 16 years. By meticulously mapping its path and the paths of other stars like it, scientists have been able to apply Kepler's laws in reverse. Instead of using a known mass to predict an orbit, they used the precise details of the orbit to weigh the central object. The math left no room for doubt. The only thing that could possibly contain 4 million solar masses within such a tiny volume is a supermassive black hole. This was a monumental confirmation, turning a long-held hypothesis into established fact through the unwavering predictability of orbital motion. But the story doesn't end with simple orbits. The extreme gravity so close to Sagittarius, a star, creates a natural laboratory for testing Einstein's general relativity under conditions impossible to replicate on Earth. We see this in a subtle effect called Schwarzschild precession. Just as Mercury's orbit precesses around the Sun, the orbit of S2 precesses around the black hole. However, the effect is vastly more pronounced here. With each frenetic 16-year lap, the point of its closest approach shifts slightly, tracing out a beautiful rosette pattern in the sky instead of a simple, static ellipse. This observed precession matches the predictions of general relativity perfectly, providing yet another stunning validation of the theory and showing how space-time is dramatically warped in this extreme environment. Looking to the future, astronomers eagerly anticipate even more profound relativistic discoveries. As our instruments become more sensitive, we may be able to detect the subtle effects of time dilation on these orbiting stars. From our distant vantage point, the clock on a star like S2 should appear to tick measurably slower as it screams through its perihelion, its light redshifted by the immense gravitational field it is battling. There is also the tantalizing possibility of witnessing a star venture a little too close. If one were to be pulled apart by the black hole's tidal forces, a process known as spaghettification, we would see the flash of its material heating up as it spirals into the accretion disk, offering a direct look at the physics of matter falling onto a black hole. The dynamics of our galactic center are not unique. They are a template for understanding all large galaxies. We now believe that nearly every major galaxy has a supermassive black hole at its core, and the mass of that black hole is strangely correlated with the properties of the galaxy's central bulge. This suggests a profound and co-evolutionary relationship where the black hole and its host galaxy grow together, their fates intertwined by gravity. The activity of these central black holes can dictate the very life cycle of a galaxy. When actively feeding, they can power immense jets of energy and radiation that blast out across space, heating up surrounding gas and effectively shutting down star formation by preventing the gas from cooling and collapsing. This feedback mechanism is a crucial piece of the puzzle in understanding why some galaxies are dead and elliptical, while others, like our Milky Way, remain active and spiral-shaped. Observing the heart of our galaxy is more than just an exercise in extreme astronomy. It is a direct glimpse into the engine room of galactic evolution. The intricate dance of stars around Sagittarius A star provides a masterclass in celestial mechanics, demonstrating how the fundamental laws of motion and gravity hold true even in the most violent and dense environments in the universe. It connects the physics of a falling apple on Earth to the orbit of a star just light hours from oblivion, proving the universal language of gravity and offering a front-row seat to the dynamic processes that have shaped and continue to shape the cosmos we call home. And so this grand exploration, from the serene orbits of comets to the chaotic heart of our galaxy, is accelerating at an astonishing pace, driven by a new era of technological marvels that are revolutionizing the field of celestial mechanics. We are no longer limited to what we can see with traditional telescopes or calculate with pen and paper. We now have an entire arsenal of tools that allow us to listen to the vibrations of space-time, peer into the darkest corners of the cosmos, and simulate the universe with breathtaking fidelity. This technological leap is opening frontiers we could only dream of a generation ago, pushing our understanding of cosmic motion into realms that test the very limits of physics itself. Space-based observatories are at the forefront of this revolution, free from the distorting veil of Earth's atmosphere. The James Webb Space Telescope, positioned perfectly at a Lagrange point, is a stunning example. Its infrared eyes are not just showing us beautiful pictures, they are providing exquisitely precise data on the motion of stars within distant galaxies, the subtle wobble of stars induced by orbiting exoplanets, and the composition of protoplanetary disks where new worlds are forming. This data is the raw material for celestial mechanics, allowing us to measure masses, orbital parameters, and dynamic interactions with an accuracy that was previously impossible. We are moving from simple detection to detailed characterization, building a statistical understanding of how planetary systems form, migrate, and evolve across the galaxy. On the ground, the detection of gravitational waves has blossomed into a full-fledged new field of astronomy. The initial success of LIGO and Virgo is just the beginning. Future observatories like the Space-Based Laser Interferometer Space Antenna, or LISA, will open a low-frequency window on the universe. This will allow us to hear the mergers of supermassive black holes, the in-spiral of smaller black holes into these giants, and possibly even the faint rumble from the very birth of the universe. Each signal is a rich dataset encoding the masses, spins, and distances of the colliding objects, providing a completely independent way to test general relativity and map the population of dark, massive objects that shape galactic evolution. Perhaps the most profound shift is happening not in our telescopes but in our computers. The mind-boggling complexity of the gravitational n-body problem, which has vexed mathematicians for centuries, is finally being tamed by raw computational power and artificial intelligence. Scientists can now run incredibly detailed simulations of our solar system's evolution over billions of years, not just once, but thousands of times with slightly varied initial conditions to understand its chaotic limits and long-term stability. AI algorithms are being trained to sift through mountains of astronomical data to find subtle patterns, perhaps the faint gravitational signature of the hypothetical planet 9 perturbing the orbits of distant Kuiper Belt objects, or predicting the paths of potentially hazardous asteroids with greater speed and accuracy than ever before. These are not just number-crunching exercises, they are active explorations of possibility, allowing us to test theories in a digital universe before seeking confirmation in the real one. These advancements are converging on some of the biggest mysteries in all of physics. The precise tracking of spacecraft, like the Parker Solar Probe as it dives closer to the Sun than any object before it, allows for ultra-sensitive tests of general relativity, searching for any tiny deviations from Einstein's predictions in the Sun's intense gravitational field. The enigmatic nature of dark matter and dark energy, which together make up 95% of the universe, is primarily a gravitational mystery. By meticulously mapping the motions of stars within galaxies and the expansion history of the universe itself, celestial mechanics provides the key evidence that is constraining theories about what these invisible components actually are. Looking ahead, the future of celestial mechanics is as boundless as the cosmos it seeks to understand. Missions are being planned to directly image and study Earth like exoplanets, requiring exquisite orbital precision to block out the parent star's blinding light. Concepts for interstellar probes, though far off, will rely on a deep understanding of gravitational slingshots and galactic dynamics to navigate between the stars. As our computational models grow more sophisticated, they may even help us unravel the ultimate fate of our solar system and the stability of other Earths orbiting other suns. We are entering an age where the ancient dance of the heavens is not just observed, but truly comprehended, from the gentle tug between a planet and its moon to the cosmic web of dark matter that binds the universe together, revealing an order within the apparent chaos that is more beautiful and complex than we ever imagined. This profound connection between the motion of worlds and the potential for life transforms celestial mechanics from an abstract study into a vital tool in the search for our cosmic neighbors. It's the difference between a planet simply being in the right place and it actually staying there long enough for life to take root, evolve, and flourish. We call this precious region around a star the habitable zone, where temperatures might allow liquid water to exist on a planet's surface. But location is only the first piece of the puzzle. A world could be perfectly positioned in this so-called Goldilocks zone, yet if its orbit is wildly eccentric or unstable, its chances for life plummet. Imagine a planet that swings incredibly close to its star, boiling its oceans before hurtling back out to a deep freeze where everything solidifies. Such extreme temperature swings, driven by orbital mechanics, would create a world of constant catastrophe, a place where complex chemistry, the very foundation of life, would struggle to find a steady foothold. Our own Earth is a testament to the gift of orbital stability. Our path around the Sun is nearly circular with a very low eccentricity. This means we receive a remarkably consistent amount of solar energy throughout our year. This stable input of warmth is a primary reason our climate has remained relatively temperate over billions of years, providing the long-term environmental consistency necessary for life to not only emerge but to diversify into the incredible complexity we see today. This stability isn't just luck, it's a product of our solar system's architecture. The gravitational influence of Jupiter, while immense, is mostly benign from our perspective. It acts as a gravitational shield, often absorbing or deflecting comets and asteroids that might otherwise cause catastrophic impacts, but its tug on Earth's orbit is gentle enough to prevent disruptive changes. This delicate balance showcases how the dynamics of an entire planetary system can set the stage for habitability on a single world. But stability doesn't always mean a lack of change. Some of the most intriguing possibilities for life arise from rhythmic, predictable orbital variations. Earth's climate itself is gently paced by Milankovitch cycles, slow, periodic changes in the shape of our orbit, the tilt of our axis, and the wobble of that tilt. These cycles, driven by gravitational interactions with other planets, subtly alter the distribution of sunlight on our planet over tens of thousands of years, triggering the ebb and flow of ice ages and interglacial periods. While these are major climatic shifts, they occur on a long, gradual timescale, allowing life to adapt and migrate. This is a very different reality from the chaotic, short-term orbital violence that could render a world sterile. When we look beyond our solar system, this interplay becomes the guiding principle for prioritizing which exoplanets are the most promising targets in our search. Discovering a planet of Earth-like mass in the habitable zone is an exciting headline, but astronomers immediately look to its orbital dynamics for the real story. A world locked in a resonant chain with other planets, like those in the TRAPPIST-1 system, suggests a stable, long-term configuration. Conversely, a planet with a highly eccentric orbit, or one that shows signs of gravitational perturbation from a volatile giant planet in the system, might be relegated to a lower priority, its environment likely too extreme for life as we know it. Celestial mechanics gives us the tools to read the history and predict the future of these distant worlds from light years away. Perhaps the most fascinating mechanic that can forge a habitable environment is tidal heating, a process where a planet's interior is warmed not by starlight, but by gravitational friction. This requires a very specific orbital dance, most often seen with moons orbiting gas giants. Jupiter's moon Europa is the prime example. Its orbit is not perfectly circular due to its gravitational resonance with the moons Io and Ganymede. This constant, rhythmic flexing, driven by Jupiter's immense gravity, generates immense heat within Europa's icy shell, maintaining a vast global ocean of liquid water in the complete absence of solar warmth. This subsurface sea, hidden from view but betrayed by the moon's orbital dynamics, is one of the most promising places to look for life in our entire solar system. The same process is likely at work on Saturn's moon Enceladus, where geysers of water vapor erupt from a subsurface ocean, spraying evidence of this hidden habitable zone out into space. In these dark, distant realms, it is not a star, but the precise and persistent forces of celestial mechanics that provide the energy for life. This incredible intersection of orbital motion and biology forces us to expand our definition of a habitable world. It is no longer just about a planet's distance from its star. We must now consider the gravitational personality of its entire system, the presence of stabilizing giant planets, the absence of disruptive neighbors, and the potential for tidal heating to create liquid water in unexpected places. The clockwork motion of the cosmos is not just a beautiful performance to observe, it is the fundamental director of life's potential. By understanding these rhythms and harmonies, we are learning to listen for the faintest echoes of biology in the silent, gravitational symphony of the universe. And this deep connection between the heavens and our daily existence is perhaps most profoundly felt in something we all take for granted: the very measurement of time itself. Long before we had digital clocks on our wrists, humanity's first and most reliable timekeepers were the sun, the moon, and the stars. The fundamental rhythms of our lives, the day, the month, the year, are not arbitrary human inventions. They are direct gifts from celestial mechanics, the observable cycles of our planet's rotation and its orbit around the sun. A day is one full rotation of Earth on its axis, bringing the sun back to the same position in our sky. A month finds its ancient roots in the moon's cycle of phases, a complete orbit around our world. And a year is one full revolution of Earth around the sun, the cycle that brings the seasons back around. Our most basic units of time are a direct reflection of our planet's motion in space. But translating these celestial cycles into a practical calendar is a famously messy business, a challenge that has occupied astronomers and priests for millennia. The problem is that these cycles are incommensurate. They don't divide into each other evenly. A lunar month is not 29.5 days, and a tropical year, the time from one spring equinox to the next, is not 365.25 days. This frustrating imperfection meant that a calendar based solely on the moon would slowly drift out of sync with the seasons, causing summer festivals to eventually occur in the winter. To correct for this, ancient cultures had to become sophisticated celestial mechanics. The Romans, under Julius Caesar, introduced the leap year, adding an extra day every 4 years to account for that extra quarter of a day. This Julian calendar was a huge step forward, but it was still slightly too long, accumulating an error of about 1 day every 128 years. By the 16th century, this small error had added up to a 10-day discrepancy, causing the vernal equinox to drift earlier and earlier and threatening the correct calculation of Easter. The solution was the Gregorian calendar reform, orchestrated by Pope Gregory XIII. This new system, which we still use today, introduced a more refined rule. A year is a leap year if it is divisible by 4, unless it is also divisible by 100, but not by 400. This complex-sounding rule simply fine-tunes the length of the average year to align almost perfectly with Earth's actual orbital period, a stunning achievement of applying precise astronomical observation to the organization of human society. This is celestial mechanics in its most practical form, a set of rules designed to keep our human-made calendars in lockstep with the actual motion of our planet. The grandest celestial rhythm of all is one that operates on a timescale so vast it was barely perceptible to ancient astronomers: precession. This slow, wobbling motion of Earth's axis, caused by the gravitational tugs of the sun and moon on our planet's equatorial bulge, completes one full cycle every 26,000 years. While its effects are too slow to impact our yearly calendar, precession was known to and deeply respected by ancient cultures. They observed that the position of the sun at the equinoxes slowly shifts backward through the constellations of the zodiac over centuries. This meant that the North Star changes over time, while Polaris marks our north celestial pole today. In ancient Egyptian times, the star Thuban was the pole star, and in 14,000 years it will be Vega. This slow drift of the heavens was encoded in myths and meticulously tracked through the alignment of massive stone monuments. Structures like Stonehenge in England or the Sun Dagger at Choco Canyon in New Mexico are not just primitive temples, they are sophisticated astronomical observatories built of stone. Their carefully placed pillars and apertures were designed to frame the rising sun on the solstice or to mark the extreme positions of the moon's orbit, events that also shift subtly due to precession. The Maya in Central America developed a calendar system of breathtaking complexity, interlocking the solar year with a sacred calendar and a long count that tracked these grander cosmic cycles. Their pyramids were often precisely aligned to cast shadows that would slither down the steps to touch a carved serpent's head only on the equinoxes. These ancient engineers were masters of practical celestial mechanics, using their understanding of orbital motion and precession to anchor their culture, religion, and agriculture to the reliable rhythms of the cosmos. In our modern world, this relationship has evolved but is no less dependent on the heavens. The global network of GPS satellites that guides our cars and phones is a testament to this. Each satellite contains an incredibly precise atomic clock, but for the system to provide accurate positioning down to a few meters, it must account for the effects of both special and general relativity. Because the satellites are moving at high speed relative to us on the ground, their clocks run slower due to special relativity. But because they are also farther from Earth's gravitational well, their clocks run faster due to general relativity. The net effect is that the satellite's clocks gain about 38 microseconds per day compared to clocks on the ground. If this relativistic correction weren't programmed into the system, the GPS would accumulate errors of over 10 kilometers per day, rendering it utterly useless. Our most advanced navigation technology only works because it is meticulously synced to the warping of spacetime described by Einstein's theories, a direct and daily application of the most profound principles of celestial mechanics. From the stone circles of our ancestors to the atomic clocks in orbit, our attempt to measure and mark time remains an eternal conversation with the motion of the heavens. These spectacular celestial light shows are far more than random streaks of light. They are a direct and beautiful consequence of our planet's journey through the leftover debris of wandering comets and asteroids. A meteor shower occurs when Earth, on its own predictable orbit around the Sun, plows through a stream of dusty particles scattered along the path of another celestial object. As these tiny particles, often no larger than a grain of sand, slam into our atmosphere at tremendous speeds of tens of kilometers per second, the friction with the air superheats them, causing them to vaporize in a brilliant flash of light that we see as a shooting star. During a shower's peak, we can see dozens of these meteors per hour, all appearing to radiate from a single point in the sky, a perspective effect that occurs for the same reason that snowflakes appear to come from a single point directly ahead of you when you're driving through a storm. The character and intensity of each shower are dictated entirely by the orbital mechanics of its parent body. The most prolific and reliable showers, like the Perseids every August or the Geminids in December, are caused by comets. As a comet journeys around the Sun, the intense solar heat vaporizes its icy surface, releasing countless particles of dust and rock that continue to trail behind it, spreading out over time to form a vast, rippled river of debris along the comet's orbital path. When Earth's orbit intersects this river, we get a meteor shower. The timing of the shower is exquisitely predictable because it happens at the exact same point in Earth's orbit each year. The specific comet responsible for the Perseids is Swift-Tuttle, a massive object that takes about 133 years to orbit the Sun, constantly replenishing the dust trail we pass through. The Geminids are a fascinating exception, originating not from a comet but from an asteroid-like object called 3,200 Phaethon, which may be a rocky comet nucleus that has lost all its ice, still shedding dust through cracking and fracturing as it swings close to the Sun. The density of the debris stream within the comet's orbit determines the shower's intensity. Most years, we pass through a relatively diffuse part of the stream, resulting in a good, standard show. But sometimes, Jupiter's gravity can perturb the stream, concentrating the particles into a denser clump. If Earth's path intersects one of these denser patches, we are treated to a meteor storm, where the sky can be filled with thousands of meteors per hour. This famously happened with the Leonid meteor shower, which originates from Comet Tempel-Tuttle in the years 1833, 1966, and 2001. Astronomers can now forecast these outbursts with impressive accuracy by modeling the gravitational influences on the debris trail over centuries, a stunning application of celestial mechanics to predict a cosmic light show. Beyond their beauty, meteor showers are a powerful scientific tool. By observing the paths and composition of meteors, we can analyze the leftover building blocks of the solar system without ever having to send a spacecraft to a comet. Spectroscopy of the light from burning meteors can reveal the chemical elements within them, telling us what these distant visitors are made of. Furthermore, mapping the distribution of meteor streams helps us create a three-dimensional chart of debris within our solar system, tracing out the orbits of their parent comets long after the comets themselves have departed for the outer darkness. This helps us understand the dynamical history of our cosmic neighborhood and the ongoing process of how small bodies evolve and disintegrate over time. Every time we look up at a meteor shower, we are witnessing a fleeting moment of contact with another world, a beautiful and fiery intersection of our planet's path with the ghostly trail of a distant traveler, a perfect demonstration of how our motion is forever intertwined with the broader dance of the solar system. But our journey through the gravitational architecture of the solar system doesn't end with Neptune. Far beyond the orbit of the last giant planet lies a vast, frigid frontier, a sprawling disk of icy remnants that serves as a permanent record of our solar system's earliest days. This is the Kuiper Belt, a region stretching from about 30 astronomical units out to roughly 55, populated by countless frozen worlds, including the beloved dwarf planet Pluto. Think of it not as an asteroid belt, which is made of rock and metal, but as a colossal deep freeze preserving the original icy building blocks that never coalesced into a major planet. This isn't a static repository, though. It's a dynamic zone whose structure and population have been meticulously sculpted by gravity over billions of years, primarily by the distant but powerful influence of Neptune. The story of the Kuiper Belt is inextricably linked to the migration of the giant planets. During the solar system's violent youth, as Jupiter and Saturn shifted their positions, Neptune was pushed outward from its formation point. As it migrated, its immense gravity began to orchestrate the motion of the countless icy planetesimals in its path. Some of these objects were captured into stable gravitational agreements known as mean motion resonances. A resonant object like Pluto is locked in a synchronized dance with Neptune. For every 2 orbits Neptune completes, Pluto makes exactly 3. This precise timing ensures that whenever Pluto crosses Neptune's orbital path, the giant planet is always on the opposite side of the Sun, a perfect cosmic avoidance maneuver that has kept Pluto safe for eons. This resonance creates stability, shepherding a whole population of objects, now called Plutinos, into similar, safe orbits. But not all objects were so fortunate. Neptune's outward journey acted like a gravitational plow, and many icy bodies that encountered it were not captured into resonance but were instead violently scattered. These scatterings imparted tremendous energy, flinging objects into wildly eccentric and highly inclined orbits, creating a distinct population known as the scattered disk. Objects out here, like the dwarf planet Eris, follow paths that are dramatically stretched into long ellipses. They spend most of their time in the cold, dark depths hundreds of astronomical units from the Sun, only diving briefly into the planetary region before swinging back out again. Their orbits are also often tilted significantly relative to the flat plane of the solar system, a telltale sign of a violent gravitational encounter in their past. The scattered disk is the solar system's gravitational badlands, a region of chaotic and unstable orbits populated by the survivors of Neptune's ancient clearing operation. The distribution of objects within these regions is not random. It is a frozen map of past gravitational events. Astronomers have found that the Kuiper Belt has a surprisingly sharp outer edge around 50 astronomical units. This Kuiper cliff is difficult to explain through the gravity of the known planets alone, and is one piece of evidence that has led scientists to hypothesize the existence of a large, undiscovered planet, often called Planet 9, lurking in the extreme outer solar system, its gravity shepherding the inner edge of this distant population. Furthermore, the way orbits are grouped by inclination and eccentricity provides a forensic record of how Neptune's migration proceeded, whether it was a smooth and steady process or a more abrupt, jump-like movement caused by close encounters with other large bodies. Studying the dynamics of these distant icy bodies does more than satisfy our curiosity about the solar system's history. It also answers a very practical question about our own neighborhood. Where do comets come from? The short-period comets, those with orbits lasting less than 200 years, originate primarily from the scattered disk. Gravitational perturbations, often from Neptune itself or from interactions with other Kuiper Belt objects, can nudge a scattered disk object inward, placing it on a new path that brings it into the inner solar system where the Sun's heat transforms it into the glorious comet we see. The Kuiper Belt and scattered disk are thus the primary reservoirs for these cosmic visitors, and their dynamics act as the delivery mechanism, gently kicking objects out of their stable orbits and sending them on a sunward journey. This intricate gravitational interplay ensures a steady supply of comets, each one a time capsule from the solar system's birth, delivered to our doorstep by the silent, persistent forces of celestial mechanics. Now let's bring our focus closer in to one of the most breathtaking and dynamically complex sites in our solar system, the magnificent rings of Saturn. From a distance, they appear as a single, solid, and flawless disk of light, but in reality, they are a vast, churning sea of countless individual particles, each one a tiny moonlet following its own independent orbit around the planet. This isn't a static jewelry display. It's a vibrant and constantly evolving system, a masterclass in orbital mechanics playing out on a miniature scale, where the delicate balance between gravity, momentum, and collision dictates every single feature we see. The first key to understanding rings is to recognize that every single particle within them is an individual satellite, obediently following Kepler's laws. Particles closer to Saturn orbit faster, while those farther out move more slowly, just as Mercury orbits the Sun faster than Neptune does. This difference in orbital speed based on distance is called Keplerian shear, and it has a profound consequence. It means ring particles are constantly rubbing past one another. This shearing motion would naturally cause the rings to spread out over time, diffusing into an ever wider and fainter disk. The fact that we see rings with such sharp, well-defined edges tells us immediately that something must be actively confining them, holding this delicate structure together against the relentless tendency to disperse. This is where the concept of shepherd moons comes into play, one of the most elegant demonstrations of gravitational resonance. These are small moons that orbit within or just alongside the rings, and their gravitational influence acts like a celestial sheepdog, herding the ring particles and maintaining those incredibly sharp edges. A perfect example is Saturn's moon Pan, which orbits directly within the Inca gap in the ring. As Pan travels around Saturn, its gravity repeatedly tugs on the ring particles at the same orbital location. This regular, periodic kick creates a gravitational resonance that clears out any particles that might wander into the gap, effectively sculpting and maintaining its pristine, empty space. It's a stunningly precise process, a gravitational feedback loop that has likely been operating for millions of years. But moons don't just create gaps, they can also generate beautiful, intricate waves within the ring material itself. As a moon orbits, its gravity can pull groups of particles slightly out of their circular paths, creating a spiral density wave that propagates through the rings, much like a spiral arm in a galaxy. These waves are not just visual curiosities. By carefully measuring their spacing and structure, planetary scientists can actually weigh the moon that caused them and determine the mass distribution within the rings themselves. It's a form of celestial seismology, where we read the gravity waves to understand the properties of the objects that created them. The very existence of these vast ring systems also poses a fascinating question of longevity and origin. Are these ancient primordial structures dating back to the formation of Saturn itself, or are we looking at a relatively recent and transient phenomenon? The evidence increasingly points to the latter. Ring particles are constantly being darkened by micrometeorite dust and are slowly spiraling inward toward the planet due to subtle drag forces. To still appear so bright and extensive today, the rings likely need a source of replenishment. The prevailing theory is that most rings are the shattered remains of a former moon that ventured too close to its planet. When an icy moon crosses inside the Roche limit, the critical distance where a planet's tidal forces overcome the moon's own gravity, it is systematically torn apart. The debris from this catastrophic disruption is then sheared out into a disk, eventually settling into the orderly yet dynamic ring structures we observe. This means we might be witnessing the aftermath of a spectacular cosmic demolition, a destructive event that gave birth to one of the most beautiful sights in the heavens. By studying these processes up close with missions like Cassini, we gain invaluable insights that reach far beyond Saturn. The physics of how ring particles collide, stick together, and are shepherded by gravity is a direct analog for the processes that occurred in the protoplanetary disk around our young sun. In the rings, we can watch in real time the fundamental mechanics of accretion, the first steps of how dust grains grow into larger bodies. It's a natural laboratory that shows us why some material remains as fine dust while other particles clump together, helping us understand why our solar system has planets instead of just a giant, featureless ring of debris. The dazzling rings of Saturn are far more than a pretty picture. They are a dynamic and ever-changing cosmic workshop, offering a front-row seat to the forces that build and shape worlds. But perhaps one of the most critical and practical applications of all this celestial knowledge lies in a field known as planetary defense, the science of predicting and potentially preventing asteroid impacts with Earth. This isn't science fiction. It's a real-world endeavor that relies entirely on the precise principles of celestial mechanics to safeguard our planet. The process begins with discovery, with telescopes constantly scanning the skies to catalog near-Earth objects, or NEO. But simply finding an asteroid is just the first step. The real challenge is using those initial observations to calculate its future path with enough accuracy to know if it represents a threat decades or even a century from now. This is where orbital mechanics gets incredibly complex. Predicting an asteroid's trajectory is not as simple as drawing an ellipse and letting it run. These objects are subject to a constant barrage of subtle gravitational nudges from the planets, especially Jupiter and Mars, which can gently perturb their orbits over time. Mission planners must run incredibly sophisticated computer simulations that account for the gravitational influence of every major body in the solar system to project an object's path into the distant future. These aren't single calculations. They're thousands of simulations run with slightly varied initial conditions to create a statistical map of possible future pathways, known as a probability cone. The goal is to see if that cone of possibility intersects with Earth's orbit at any point. Adding another layer of complexity is a fascinating and subtle non-gravitational force called the Yarkovsky effect. This occurs when an asteroid absorbs sunlight on its day side and then re-radiates that energy as heat as it rotates onto its night side. This tiny push from thermal radiation acts like a miniature, continuous thruster, very slowly but persistently altering the asteroid's orbit over years and decades. For a large asteroid, this effect might seem negligible, but over the long timescales involved in impact prediction, it can mean the difference between a miss and a direct hit. Accounting for the Yarkovsky effect requires knowing not just the asteroid's size and orbit, but also its rotation period, spin axis orientation, and surface composition details that often require dedicated radar observations or space missions to determine. This immense effort is coordinated globally, with NASA, a Planetary Defense Coordination Office, and similar groups around the world constantly monitoring the ever-refined risk assessments. When a new object is discovered, its potential risk is ranked on scales like the Torino scale or the more technical Palermo scale. The vast majority of objects score a 0, indicating no hazard. But for the very few that show a non-zero probability of impact, the focus shifts from observation to mitigation. The successful Double Asteroid Redirection Test, or DART mission, was a stunning proof of concept for this very idea. By crashing a spacecraft into the small moonlet of the asteroid Dimorphos, scientists weren't trying to blow it up. They were using celestial mechanics to precisely alter its orbital period around its larger companion. The mission was a resounding success, demonstrating that we can indeed use a kinetic impactor to nudge an asteroid's trajectory, a technique that could one day be used to deflect a genuinely hazardous object away from a collision course with Earth. This entire field transforms celestial mechanics from an abstract study of cosmic motion into a vital planetary insurance policy. It demonstrates that understanding the gravitational dance of the solar system is not just about satisfying our curiosity about the past, it is fundamentally about securing our future. By meticulously tracking these distant rocks and calculating their paths with ever greater precision, we are using the laws of physics themselves to watch over our world, ensuring that the same forces that govern the stars are harnessed to protect the life thriving on our pale blue dot. While we often picture our solar system as a self-contained neighborhood with the sun at its center, this entire magnificent structure is itself in motion, swept up in a far grander gravitational dance. Our Sun, along with its planetary entourage, is orbiting the center of the Milky Way galaxy, traveling at a breathtaking speed of over 500,000 miles per hour. Even at this incredible pace, the journey is so vast that a single complete revolution, known as a cosmic year, takes approximately 230 million years. The last time our solar system was in this same position within the galaxy, the dinosaurs were just beginning their reign on Earth. This galactic orbit means we are perpetually under the influence of the combined gravity of hundreds of billions of stars, vast clouds of gas, and most significantly, the immense, invisible halo of dark matter that makes up the majority of the galaxy's mass. This overarching galactic gravity plays a crucial role in shaping the outermost reaches of our own system, particularly the distant Oort cloud. The gravitational pull from the Milky Way as a whole helps to define the Oort cloud's spherical structure and sets the boundary where the Sun's influence finally yields to that of the galaxy. But this relationship is dynamic, not static. As we travel through the galaxy, the subtle, shifting tides of the Milky Way's gravity can perturb the delicate orbits of these icy bodies. Just as the Moon's gravity raises tides on Earth, the galactic tide can gently squeeze and distort the Oort cloud. This periodic squeezing is thought to dislodge comets from their stable orbits, sending them on a long fall inward toward the Sun. Some scientists propose that these gravitational tides may be responsible for periodic showers of comets into the inner solar system, which could correlate with historical mass extinction events on Earth, linking the grandest scale of celestial mechanics directly to the history of life on our planet. Our motion isn't a simple, flat circle around the galactic center. The solar system also performs a gentle, wave-like oscillation, bobbing up and down through the plane of the Milky Way disk. We cross through this dense central plane approximately every 30 to 40 million years. This vertical journey may have profound consequences for Earth's climate. The galactic plane is a region much richer in interstellar gas, dust, and potentially stronger gravitational fields. Some theories suggest that as we pass through this denser region, the protective heliosphere generated by the solar wind could be compressed, potentially allowing more interstellar material and high-energy cosmic rays to reach the inner solar system. An increased flux of cosmic rays could, in turn, influence cloud formation in Earth's atmosphere, potentially leading to climatic cooling and triggering ice ages. This fascinating hypothesis connects our vertical galactic motion to long-term climate cycles on our planet, a stunning example of how celestial mechanics on a galactic scale can touch the very environment we live in. This perspective completely redefines our sense of place. We are not just inhabitants of a planet orbiting a star. We are passengers on a star that is itself orbiting a galactic center, all while moving through a universe filled with invisible matter and energy. The same gravitational force that holds us in our chairs governs the motion of our planet, the orbit of our Sun, and the majestic rotation of our entire galaxy. It is a unified force operating seamlessly across every scale of existence, from the falling of an apple to the dance of galaxies. Understanding these large-scale dynamics allows us to see the solar system not as an isolated island, but as an integrated part of a much larger and dynamic cosmic structure, forever moving within the graceful, invisible currents of the Milky Way's gravitational field. But this elegant gravitational choreography doesn't just govern the paths of worlds, it can also lock their very spin, synchronizing their rotation with their revolution in a mesmerizing state known as spin-orbit resonance. The most familiar example of this is our own Moon, which has become tidally locked with Earth, always presenting the same cratered face to us as it orbits. This isn't a coincidence, it's the inevitable outcome of a gentle but persistent gravitational tug-of-war. The process begins with a simple asymmetry. No celestial body is a perfect, uniform sphere. Earth has slight bulges and the Moon has mass concentrations called maskons. As the Moon rotated independently in its youth, Earth's gravity would pull on these bulges, trying to align them with the line connecting the two centers of mass. This constant off-center pulling creates a torque that acts as a brake on the Moon's rotation. Over hundreds of millions of years, this tidal friction dissipated the Moon's rotational energy through internal heat, gradually slowing its spin until it perfectly matched its orbital period. Once this one-to-one resonance was achieved, the bulges were permanently aligned, the torque vanished, and the Moon was locked, forever keeping one hemisphere a mystery to Earth-bound observers until the space age. This same process has shaped countless other relationships in our solar system. Almost every major moon is tidally locked to its parent planet. Jupiter's large Galilean moons, from volcanic Io to icy Europa, all keep one face pointed toward the gas giant as they orbit. Even Pluto and its large moon Charon are locked in a mutual embrace, having achieved a double tidal lock where they both always show the same face to each other as they orbit a common point in space between them. But the story doesn't always end with a simple one-to-one ratio. Take Mercury, the innermost planet. For a long time, astronomers thought it was tidally locked with the Sun, showing one scorching hot face and one perpetually cold face. However, radar observations in the 1960s revealed a much more fascinating and complex reality. Mercury is locked in a 3-to-2 spin orbit resonance. It rotates on its axis exactly 3 times for every 2 revolutions around the Sun. This means a single day on Mercury, from one sunrise to the next, lasts 2 of its years. This peculiar state arose because of Mercury's highly elliptical orbit. The strength of the Sun's tidal force varies dramatically as Mercury swoops close and then swings far away. This variation prevented the simpler one-to-one lock and instead allowed it to settle into this stable 3-beat rhythm, a cosmic waltz between its spin and its path. The implications of being locked in such a resonance extend far beyond just which side faces forward. They can fundamentally dictate a world's environment and geology. For a moon like Jupiter's Io, being locked in a one-to-one resonance with its massive parent is only part of the story. Its orbit is also perturbed by the other large moons, Europa and Ganymede, in a gravitational partnership called the Laplace resonance. This additional dynamic stress, combined with the constant flexing from Jupiter's tidal pull, generates immense internal friction. This friction is the engine behind Io's spectacular and relentless volcanic activity, making it the most geologically active body in the entire solar system. Its surface is a constantly changing landscape of lava lakes and erupting plumes, all powered by the energy of its locked orbit. For a planet tidally locked to its star, the consequences are even more extreme. One hemisphere would be locked in perpetual, blazing daylight, while the other would be trapped in an eternal, frigid night. The only potential for a temperate zone would be a thin, twilight band along the terminator line where the two extremes meet. This drastic temperature difference could drive incredibly powerful supersonic winds around the planet as the atmosphere tries to equalize the immense heat imbalance, creating a world of permanent, violent storms. Understanding these resonant states is therefore crucial as we search for life beyond our solar system. Many of the most promising exoplanet candidates orbit dim red dwarf stars. Because these stars are so faint, their habitable zones are very close in, a region where tidal forces are exceptionally strong. This makes it highly probable that any Earth-sized world found there will be tidally locked. Instead of a 24-hour cycle of day and night, such a planet would have a permanent day side and a permanent night side. For life to arise and persist, it would have to adapt to conditions utterly alien to our experience, potentially huddling in that narrow, fragile strip between the scorching light and the endless dark. The physics of spin-orbit resonance thus moves from an abstract orbital curiosity to a central factor in planetary habitability, a fundamental process that can determine whether a distant world is a hellscape of extremes or could possibly harbor the delicate conditions necessary for life to begin. Yet the serene, stately orbits of stars within a single galaxy are just one part of a far more dynamic and often violent cosmic story. On the grandest scales, galaxies themselves are not isolated islands. They are social creatures drawn together by gravity into groups and clusters, and within these dense neighborhoods, close encounters are inevitable. Galactic collisions and mergers are among the most spectacular events in the universe, transformative processes where the collective gravity of billions of stars orchestrates a slow-motion ballet of creation and destruction that unfolds over hundreds of millions of years. What's truly counterintuitive about these colossal encounters is that they are not like two cars crashing on a highway. The spaces between stars are so vast that actual stellar collisions are incredibly rare. Instead, a galactic merger is a gravitational event, a profound interaction where the invisible forces of dark matter and the collective pull of countless stars completely reshape both systems without their individual members ever touching. The drama begins as two galaxies first approach each other. Their immense halos of dark matter, which make up the bulk of their mass, are the first to interact, their gravitational fields beginning to tug and distort one another long before the visible disks overlap. As they draw closer, these tidal forces become overwhelming. Imagine the gravitational pull from the approaching galaxy being stronger on the near side of its neighbor than on its far side. This difference in force stretches and distorts the galaxies, pulling long streamers of stars, gas, and dust out into space. These magnificent structures are called tidal tails, and they are the hallmark signature of a galactic interaction, beautiful celestial ribbons that can extend for tens of thousands of light years. The iconic antennae galaxies are a perfect example. They're two long, arcing tails of stars flung out into the void, giving them their insect-like name and providing a stunning snapshot of this initial gravitational tug-of-war. As the galaxies plunge through each other, their clouds of interstellar gas and dust experience this gravitational chaos most directly. Unlike stars, which simply slide past one another in their new, distorted orbits, these gas clouds can collide. When they do, they create immense shock waves that compress the gas, triggering violent and prolific waves of new star formation. These bursts of creation, known as starbursts, can light up the interacting galaxies, creating brilliant blue knots of young, massive stars. For a time, the galaxy becomes a stellar nursery operating at a frenzied pace, far exceeding the normal rate of star birth seen in an isolated spiral galaxy. This is a beautiful irony. The destructive act of a collision becomes one of the universe's most powerful creative forces, seeding the future with new generations of stars. The fate of the galaxies is ultimately sealed by a subtle but relentless process called dynamical friction. This isn't friction in the everyday sense of two surfaces rubbing together. Instead, it's a gravitational effect. As the two galaxies interpenetrate, the stars and dark matter of the smaller galaxy create a kind of gravitational wake in the halo of the larger one. This wake exerts a drag force on the smaller galaxy, steadily sapping its orbital energy and angular momentum. Think of a spoon moving through a jar of honey. The honey pulls back on the spoon, slowing it down. Dynamical friction acts in a similar way, causing the orbits of the two galaxies to decay. They don't just swing past each other and fly apart. They are doomed to fall back together, again and again, with each passage further eroding their structure until they lose their individual identities entirely. After multiple close passes over hundreds of millions of years, the two systems finally merge into one. The elegant spiral structures are completely erased, their delicate orbits scrambled into a new, random configuration. The end product of this cosmic consolidation is often a giant elliptical galaxy, a featureless, football-shaped swarm of stars following chaotic orbits in all directions. These elderly red and yellow galaxies that dominate the centers of rich clusters are not primordial. They are the products of this violent hierarchical growth, the final testament to a history of mergers. At the very heart of this new galaxy, another dramatic merger is often taking place. Most large galaxies host a supermassive black hole at their center. As the galaxies merge, their central black holes sink to the core of the new system through dynamical friction. There, they form a binary pair, orbiting each other and eventually merging themselves in an event so cataclysmic it shakes the very fabric of space-time, sending out powerful ripples known as gravitational waves. Our entire understanding of this billion-year process is built upon the foundation of celestial mechanics and immense computer simulations. Astrophysicists use n-body codes that model the gravitational interactions between millions of point masses representing stars and dark matter particles. They add in the hydrodynamics of colliding gas clouds and the feedback from newly formed stars and black holes. By running these simulations with different initial conditions varying the collision speed, the angle of approach, the mass ratios, they can create a library of possible outcomes. Then they compare these digital universes to the beautiful, distorted galaxies we see through our telescopes, like the mice galaxies or the tadpole galaxy. This powerful synergy between simulation and observation allows us to not only explain the strange shapes we see, but also to read the history of a galaxy by its present-day structure, understanding that the stately elliptical galaxy we see today was once a pair of vibrant spirals, forever united by the irresistible and creative force of gravity. Yet for all the power of gravity to pull galaxies together in majestic mergers, an even more profound and mysterious force is working on the grandest stage of all, operating on a scale that defies our everyday intuition. This is dark energy, a mysterious presence that seems to be doing the very opposite of gravity. It's pushing the universe apart at an ever-increasing rate. While gravity sculpts stars, planets, and galaxies, dark energy dictates the ultimate fate of the entire cosmos, and it's through the precise tools of celestial mechanics that we first detected this enigmatic force and began to unravel its implications. The story of this discovery is a testament to meticulous observation and the power of applying orbital mechanics to the largest structures imaginable. In the late 1990s, two independent teams of astronomers were using distant supernovae, specifically a type called Aya supernova, which have a known intrinsic brightness, to measure the expansion history of the universe. They were essentially using these exploding stars as cosmic mile markers, by carefully measuring the redshift of their light, which tells us how much the universe has stretched since the explosion, and comparing it to their apparent brightness, which reveals their distance. They could chart how the expansion rate has changed over billions of years. Everyone expected to find that the expansion was slowing down, as the collective gravity of all the matter in the universe should be putting on the brakes. But the data told a shocking and counterintuitive story. The distant supernovae were fainter than expected, meaning they were farther away than they should have been if the expansion were decelerating. The only possible explanation was that the expansion of the universe wasn't slowing down at all. It was accelerating. Something was actively working against gravity, pushing galaxies apart faster and faster. This something was dubbed dark energy, and its discovery turned cosmology upside down, ultimately earning the researchers the Nobel Prize in Physics. So what does this mean for the future? If dark energy continues to dominate, as all current evidence suggests it will, the long-term forecast for the cosmos is a rather lonely and cold one, often called the Big Freeze or heat death. As the acceleration continues, distant galaxies will eventually be pushed away from us so quickly that their light will no longer be able to reach us. The observable universe will effectively shrink, even as space itself expands. Galaxies within our local group will remain gravitationally bound, but everything beyond will fade from view, their light stretched into undetectable wavelengths as they vanish beyond our cosmic horizon. Over trillions of years, star formation will cease as galaxies are pulled apart and the raw material for new stars is lost to the void. The universe will become a much darker, colder, and emptier place, a vast and increasingly diffuse sea of isolated stars and black holes slowly fading away. The role of celestial mechanics in this grand cosmic drama is absolutely fundamental. It provides the essential mathematical toolkit we use to model this expansion and test our theories. The same principles that allow us to calculate the orbit of a moon around a planet are scaled up to track the motion of entire galaxies through expanding space. The Friedmann equations, which are derived from Einstein's equations of general relativity, are the celestial mechanics of the universe itself. They describe how the scale of the universe changes over time based on its contents, matter, radiation, and this mysterious dark energy. By plugging in observations from supernova, the cosmic microwave background, and the large-scale distribution of galaxies, we can solve these equations to measure the properties of dark energy with ever-increasing precision, determining its strength and whether it changes over time. This is where the challenge becomes one of the greatest in all of modern physics. Is dark energy a constant force, represented by Einstein's cosmological constant, or is it a dynamic field that evolves, perhaps growing stronger or weaker over time? Answering this question requires a breathtaking synthesis of disciplines. We need the precise orbital mechanics to track the motions of standard candles like supernova across billions of light years. We need general relativity to understand the curvature and expansion of spacetime itself, and we need cutting-edge observational astronomy to gather the data from telescopes on the ground and in space. Projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory are conducting vast, deep surveys of the sky, mapping the positions and motions of millions of galaxies to measure the history of cosmic expansion with unprecedented detail, using the universe itself as a laboratory to probe the nature of this mysterious force. Ultimately, the quest to understand dark energy brings us to the very edge of known physics, confronting us with a reality where the vacuum of empty space itself seems to possess a repulsive energy. It's a humbling reminder that the forces governing the cosmos are far more complex and bizarre than we once imagined, and that the same principles of motion that guide a planet in its orbit are also the key to unlocking the deepest secrets of the universe's beginning, its evolution, and its ultimate distant fate. And so the timeless principles that guided ancient mariners by the stars are now being encoded into the flight plans of tomorrow's interstellar pioneers. As humanity sets its sights on destinations beyond the comfortable embrace of Earth's gravity, the abstract equations of celestial mechanics transform into the most practical of roadmaps. The future of human space travel isn't about building ever more powerful rockets to blast our way through the cosmos. It's about becoming savvy navigators of the gravitational currents that flow between the planets and stars. This is a journey of finesse, not just force, where a deep understanding of orbital dynamics will be the difference between reaching new worlds and being lost in the void. Consider the immense challenge of a crewed mission to Mars. The journey isn't a simple straight line. It's a carefully calculated arc known as a Hohmann transfer orbit, an energy-efficient path that uses the sun's gravity as a guiding hand. Launch windows for such a trip don't open every day, but once every 26 months, when the relative positions of Earth and Mars allow for this minimal energy trajectory. But even this is just the beginning. Future Martian colonists won't just be going for a visit, they'll be establishing a permanent presence. This requires a constant stream of supplies, habitat modules, food, rovers, and return vehicles, all of which must arrive on a precise schedule. Managing this interplanetary supply chain will demand an intricate understanding of orbital mechanics, with cargo vessels launched on various transfer orbits to ensure a steady, predictable arrival at the red planet, much like a carefully timed conveyor belt operating across hundreds of millions of miles of space. The true magic of this new era will be our sophisticated use of gravity assists and Lagrange points. These aren't just tricks for robotic probes anymore. They will be the interstates and way stations for human expansion. A spacecraft bound for the outer solar system might first swing by Venus to pick up speed, then use Earth for a second gravitational kick, all before finally heading toward Jupiter. This celestial pinball game dramatically reduces the fuel required, making ambitious missions feasible. Meanwhile, the stable Lagrange points in the Earth-Moon system, particularly L4 and L5, are poised to become the first off-world hubs. These gravitational oases of stability are ideal locations for constructing large space stations, fuel depots, and shipyards. Here, in the deep silence of space, we could assemble massive interstellar arcs or service deep space vessels, using these points as stepping stones and safe harbors, effectively creating the first permanent infrastructure beyond Earth's immediate grasp. Perhaps the most visionary application of these principles lies in the realm of interstellar travel itself. Projects like Breakthrough Starshot aim to send tiny, gram-scale probes to our nearest stellar neighbor, Alpha Centauri, within a single generation. The concept is breathtakingly simple yet fiendishly complex. A powerful ground-based laser array would fire at a light sail attached to a tiny probe, accelerating it to a significant fraction of the speed of light within minutes. But once this nanocraft is hurled into the abyss, how does it navigate a 4-year journey across trillions of miles? There are no road signs in interstellar space. Its navigation system would have to be autonomous, using the precise relative positions of the stars themselves as its guide. By continuously tracking the apparent shifts of nearby stars against the background of more distant galaxies, this tiny probe could triangulate its position and correct its course with microscopic thrusters, performing celestial mechanics on a galactic scale. Back in our own solar system, any future colony on the Moon or Mars will live and die by its mastery of orbital knowledge. Communication with home will rely on a complex ballet of satellites in carefully choreographed orbits to ensure a constant, unbroken link with Earth. The mining of resources, such as water ice from permanently shadowed lunar craters or the Martian poles, will require precise orbital calculations to get those valuable commodities to orbital processing stations or onward to other colonies. Even the simple act of landing and taking off becomes a high-stakes exercise in physics. The thin atmosphere of Mars and the complete lack of one on the Moon mean that landers can't rely on aerobraking alone. They must execute perfectly timed powered descents and ascents, their trajectories calculated to the second to conserve every precious drop of fuel. This next great chapter of exploration, from settling Mars to touching another star, will not be written by the loud roar of engines alone, but by the silent, unwavering logic of gravitational fields and orbital pathways. We are learning to listen to the subtle music of the spheres and to dance to its rhythm. By mastering the celestial mechanics that have governed the cosmos since its beginning, we are not conquering space, but rather learning to live within it, turning the fundamental forces of the universe into our most powerful allies on the journey to becoming a multi-planetary and eventually an interstellar species. From the graceful arcs of planetary orbits to the cataclysmic dances of merging galaxies, the story of celestial mechanics is ultimately a story of connection, a revelation that the universe, in all its apparent complexity, operates on a set of elegant, universal rules. We've journeyed together from the foundational pull of gravity that holds worlds in their courses to the conservation of angular momentum that spun a cloud of dust into a solar system, and from the stabilizing harmonies of orbital resonance to the unpredictable chaos of three-body interactions. These are not just abstract concepts confined to textbooks. They are the active, dynamic forces that sculpted the rings of Saturn, that power the volcanoes of Io, that guide our spacecraft to other worlds, and that will one day perhaps carry our first probes to the stars. This incredible journey of understanding, from Newton's falling apple to Einstein's curved spacetime, represents one of humanity's greatest intellectual achievements. It's a testament to our relentless curiosity, our drive to measure, to calculate, and to decode the cosmos. We've learned to predict eclipses millennia in advance, to discover unseen planets by the wobbles they impart on their neighbors, and to listen for the faint ripples in spacetime from collisions that happened over 1 billion years ago. We have, in a very real sense, learned to speak the universe's native language of mathematics and motion. And yet, for all we have learned, the cosmos retains its deepest secrets. The ghostly grip of dark matter, which we can only detect by its gravitational whisper, and the mysterious repulsive force of dark energy, which pushes the very fabric of the universe apart, are humbling reminders that our map of reality is still incomplete. These are not roadblocks, but rather the next great frontiers, inviting a new generation of thinkers, observers, and explorers to push the boundaries even further. So the next time you find yourself under a clear night sky, take a moment to truly look up. See not just a random scattering of lights, but a grand, interconnected clockwork of immense scale and beauty. Each point of light is a sun, likely with its own family of worlds, each moving to the same rhythm of gravity that governs our own place in space. That sense of wonder you feel is the beginning of understanding. It is the spark that has driven every discovery, from the first stargazers to the modern scientists peering through our most powerful telescopes. Keep nurturing that curiosity, keep asking questions, and never stop marveling at the fact that we are part of a universe capable of contemplating its own existence. The greatest journey of discovery is far from over. In many ways,